Okay, so let's see what the media is talking about today. A map reveals a cosmic void where laws of physics seem not to apply. Dark matter findings suggest Einstein may be wrong. It's gonna be one of those days again. Anyway, hello wonderful person. Just like every science communicator, at some point in life I learned that as soon as you mention Einstein was wrong, or talk about how laws of physics might be broken somewhere, it definitely captures everyone's attention. But I guess at some point you also start feeling really guilty about those headlines, and so I'm gonna try to avoid doing that in this video. But we are actually going to be discussing these particular findings because they are absolutely fascinating and, well, unfortunately do not actually prove Einstein wrong. As a matter of fact, quite the opposite, they prove him extremely correct. And they also show us that we sort of understand the universe extremely well. However, in this particular finding, there is one unusual discovery. I'll mention this near the end of the video. So what exactly are we talking about? We're talking about the Dark Energy Survey, also known as DES for short. And this is probably one of the biggest collaborations on the planet, except for maybe some of the other ones like the Event Horizon Telescope, that involved 7 different countries, 25 different institutions, and over 400 different scientists, some of whom you see right here in this picture. And the purpose of this survey, along with the actual studies behind it, is to kind of establish if we understand the universe, and if we understand what's happening in the universe, by trying to compare the theories of the universe, and specifically the theory we usually refer to as the Lambda CDM model of cosmology, and compare and contrast this model to the actual observations from different telescopes. Now in this particular case though, they only used one major telescope located in Chile, this one right here, and the telescope here is really famous because it also has this extremely powerful digital camera attached to it. A camera that they refer to as dark energy camera. And the purpose of the camera, as the name suggests, is to study the dark energy, the mysterious, I guess, substance or something that seems to cause the universe to expand faster. And because this camera has something like 570 megapixels in it, which is I think about 50 times more than the camera in my smartphone, and also because over the course of 6 years, from 2013 to 2019, the scientists also have been able to use this for over 750 nights in total, they were able to discover quite a lot already. Now, first of all, this is the 3rd year, the so-called year 3 of Dark Energy Survey, and here after 345 nights of observations, with about 1/8 of the night skies observed, they were able to uncover close to about 230 million different galaxies, and a lot of really interesting features in between those galaxies, including things like cosmic voids, with one visible in this particular image, and with a total number of these found standing at 3,222, while also confirming the idea behind the clumpiness of the universe, meaning that the galaxies are not just sort of evenly spread out, they are more or less clumped, forming what you see right here. This is what we refer to as the cosmic web, while at the same time also identifying several major gravitational lensing effects, all of which was exactly what they expected to find, and all of which was also required for them to confirm Einstein's theories, confirm our cosmological models, but most importantly, prove several major things. First of all, that dark matter seems to be real. As a matter of fact, this is probably the biggest proof we have right now that dark matter seems to be, well, everywhere, at least in those regions where they looked at. Or in other words, just as predicted in the Lambda CDM models, at least 25% of everything in the universe seems to be the mysterious dark matter. And the way that they were able to see this is by looking at those various galaxies everywhere, and we're talking about close to about 230 million galaxies, using the redshift of these galaxies to establish the more or less precise distance to them, and then establishing the overall mass present in those regions, by observing the weak lensing effect that you see right here, for example. This is one of many galactic clusters that have previously been discovered to have a lot of dark matter in them. And so in this image from Hubble, you can kind of see the lensing effect by something invisible but something really massive in this region right here. And so by using the combination of the gravitational lensing effects, which allowed them to more or less establish the total mass of dark matter present there, and by combining this with the observations of galactic clustering or galactic clumping, and looking back on this region right here that roughly represented the universe from today up to about 7 billion years ago, while also combining this with some really rigorous statistical analysis, which involved a lot of sort of blind analysis where you don't actually know what you're going to find, they were able to confirm some really major assumptions we had about the universe. First of all, we have to compare this to one of the previous major releases, known as the Planck collaboration. This one was using the Planck telescope to literally try to study the universe by looking at this, the cosmological microwave background, or the so-called oldest light in the universe. Now, this was a very important discovery a few years ago, and it was a very important confirmation of our theories, but this only represented a snapshot of the universe approximately 13.8 billion years ago. It was really important for the scientists to see if the original predictions from these Planck observations would actually be confirmed by observations from some of the later universe, the universe today, for example. So would something similar be visible if we look at the universe 7 billion years ago, 6 billion years ago, or even closer to today, I guess? And so for this reason, a lot of unbiased, blind statistical analysis was used to try to establish some of these parameters, including, of course, the Hubble constant that we often talk about. And well, in a nutshell, 26 out of 30 papers released so far essentially suggest that pretty much everything we believed about the universe seems to be more or less correct. So for example, if we look at the Hubble constant, or the expansion of the universe, the original value from the Planck collaboration was about 67 kilometers per second per megaparsec. In other words, for every 1 million parsec of distance, the universe expands by about 67 kilometers per second faster. In this collaboration, the value was a little bit higher, it was about 68.1, but still within the boundaries what the scientists expected it to be. Although do check out one of the previous videos where I actually go into some other studies that do talk about this mystery in a little bit more detail. But pretty much everything else in these studies suggests that our understanding of the universe from the previously mentioned lambda CDM model seem to be more or less correct. The observations in this case do indeed meet the expectations from the theories. Now obviously not everything, but for the most part they are more or less correct. There is, however, one thing that they were kind of surprised about, and this is why the publications you might have seen online mentioned Einstein being wrong and so on. The only tiny difference between the observations of Planck telescope and the more recent observations from the Dark Energy Survey seem to point at the very unusual fact that the universe seems to be a few % less clumpy than predicted. Or if we were to look at this more practically, the original models of the formation of matter in the universe and the formation of galaxies and so on does imply that everything should be a little bit more clumpy. Galaxies should be a little bit closer to one another, the cosmic web should be a little bit thinner and so on, and everything is expected to look in a certain way. But by using the observations from the last 7 billion years, the scientists discovered that the galaxy clustering was not as dramatic as they expected. Now here we're talking about just a small percentage difference, but it is significant enough to possibly create a new mystery. Something in the universe is causing the galaxies to not be as clumpy as predicted. Now obviously it does not mean that he was wrong and nothing is really wrong with the universe. It only implies that something out there is still mysterious and is not really easy to explain with just our current understanding of the cosmological theories. Something has to be modified, we're just not entirely sure what yet. No one is sure, and so it's a mystery, and naturally nobody is really wrong yet. And considering the fact that everything else in these papers seem to actually prove our ideas and our understanding of the universe, including proving the overall density of the universe, supporting the dark energy, supporting the cosmological constant, and of course predicting the relatively similar expansion of the universe as well, with just that cluster and amplitude being a little bit different from what was originally predicted, overall it presents an extremely important discovery that we sort of, as humans, tend to understand the universe really well, which is really surprising. I think a lot of scientists behind these papers were probably just as surprised that our original cosmological theories from a few decades ago seem to actually predict pretty much everything, almost perfectly. And once again, these papers prove that the dark matter seems to exist, the universe or the galaxies in the universe form the beautiful cosmic web you see right here simulated in the Illustris project, and the galaxies tend to kind of come closer together, forming large clusters that we see everywhere, with a bunch of different cosmic voids in between them, and in this case it was 3,222 cosmic voids discovered. But I guess it's also important to remember that this is just the beginning. Remember, they only covered 1/8 of the night sky, and they also started this back in 2013. After a couple of decades of doing this, we're going to have a lot of really interesting data. Possibly a lot of confirmations of theories that exist today, but possibly a lot of new mysteries that we can't even imagine yet. More importantly though, the whole purpose of this is to try to discover what's happening with this whole expansion of the universe. It's still a huge mystery, nobody really understands exactly what's happening, and there are a lot of unusual observations coming from different studies. But one of the more important confirmations coming out of this is that dark matter seems to be real after all. It seems to be everywhere. We just don't really know what it is, or what it's made out of, or how to find it. We just seem to see the effects of it. Unless, of course, this has some other explanation. Right now, there is no better explanation. But anyway, on that note, I guess first of all, congratulations to the entire team responsible for making this happen, and also, I'm actually looking forward to hearing more about the results and the discoveries coming from this incredible collaboration. At the same time, you can always check out all of this by yourself by using the links in the description, and well, it's a lot of reading, it's actually a lot of different concepts and ideas that are extremely difficult, but these concepts are slowly taking us closer and closer to basically understanding the universe as it seems to be. Not the universe we want to believe in, not the universe that some people think exists, but the actual universe as seen in the telescopes. Which of course makes this particular collaboration and these studies extremely important in helping us understand the truth of the universe. There's a really interesting experiment going on in Italy that's been trying to discover the mysterious dark matter for a few years now. And last year we've discussed one of the major announcements from this experiment that potentially identified something unexplainable. But a very recent analysis and a very recent paper, reanalyzing a lot of this data, discovered something a little bit more interesting, a little bit more intriguing, and potentially a little bit more groundbreaking. Hello wonderful person, this is Anton, and today we're going to be discussing this particular study that suggests we might have actually discovered dark energy, the concept that we kind of know even less about. So let's discuss this in more detail and talk about some of the potential discoveries coming out of the study. First of all, quick reminder, and I guess quick clarification. Dark matter, despite its somewhat unusual name, does not necessarily mean that it's some sort of a particle. It's more of a phenomenon. An unexplained phenomenon that seems to cause a lot of matter in the universe to sort of stick together a little bit more and to cause certain increases in mass where there should be none. We've discussed this idea a lot before, and I've also discussed a lot of the proofs behind this, but at the moment nobody really knows what's causing all of these effects. And so in reality, instead of calling it dark matter, we should be calling it some sort of a gravitational anomaly, or some sort of a mass anomaly. It does not necessarily mean it's made out of particles, but one of the most leading theories, and I guess some of the best explanations in regards to dark matter, do propose that it might contain some sort of a particle. Specifically, there are two major theories, either particles known as WIMPs, weakly interacting massive particles, or another concept known as Axions, both of which theoretically make sense, but neither one of which has so far been detected. Although interestingly enough, last year we've discussed this unusual detection from the experiment known as Xenon 1T. The experiment you can learn more about from one of the links in the description. In a nutshell, just like some of the previous experiments with a similar name, most of these experiments usually involve some sort of a really large tank filled with liquid xenon. With xenon being that noble gas that doesn't really react with much and generally does not produce a lot of emissions. And so if something passes through this gas, and specifically here we're talking about some sort of a dark matter particle, in theory it should create some sort of an emission. And so a lot of these tanks will also often contain some of the most advanced sensors in the world. Here's actually the image from this particular experiment, with each of these sensors being able to quite accurately detect and position every single particle that interacts with that particular tank of xenon. And to make sure that there's an actual detection and that it's not some sort of an error, normally the scientists first run the experiment by trying to measure the background radiation, and then use these measurements as a kind of a baseline in order to detect any potential extra particles then hitting the tank. And so it just so happens that the data released from last year, with the data itself representing the collection for approximately 2 years between 2016 and 2018, detected 53 extra events on top of the 232 background radiation events that were expected from this particular experiment, which presented a lot of interesting opportunities to study and to try to figure out what exactly it is that the scientists have discovered. But in order to analyze the actual interaction of particles with the tank of xenon, the scientists had to rely on the mathematical models, mostly because, well, the only data they have from all of these detections is the amount of energy that's being produced by every single particle interacting with xenon. And so if the mathematical model for example, dark matter axions matches the observations, in this case it would mean that we've finally detected dark matter. But unfortunately, the original predictions or the original analysis determined that it's very unlikely for these particular particles, these 53 extra detections, to be axions, or to be any kind of a dark matter particle that we originally predicted. Mostly because, well, there were just too many. We would require a lot more of these axions everywhere in the universe for this amount of extra detections to be then discovered here on planet Earth. Or in other words, we would just require way more dark matter everywhere. And that doesn't exactly match with the theory and the original prediction. And so a potentially different explanation was required to explain these 53 extra detections, which is what the scientists have been trying to do for the past year and a half now. They've been trying to figure out what exactly can be used to explain, and so the scientists behind the paper you can find in the description below constructed an entirely new model in order to try to explain the observations, and their physical model seems to fit almost perfectly. But strangely enough, their model does not focus on dark matter at all. It focuses on that other, even less understood concept, dark energy. Alright, so what exactly is that? Well, it's that other concept we know so little about. I think in the past I've probably made about 3 to maybe 4 videos in the last few years, and that's how little we know about dark energy. It's that stuff that we believe exists everywhere in the universe, and it's that stuff that seems to encourage and increase the acceleration of the expansion of the universe, but we don't really understand what's causing it and how exactly any of this works. We only know about this mathematically. It seems to represent approximately 68% of everything in the universe, with approximately 27% being the mysterious dark matter, and everything else being the stuff we're familiar with, the things we're made out of. But whatever dark energy is, it does seem to be an actual phenomenon as well. It seems to somehow accelerate the expansion of the universe, something that has been proven over and over again using different experiments. There's actually at least one major experiment trying to figure this out, known as the Dark Energy Survey. Ironically though, instead of discovering more about dark energy, in the past this experiment has allowed us to discover some of the least visible objects in our own solar system and also in the vicinity in our own galaxy. We still haven't really learned much about dark energy itself from this particular experiment. And generally the way that these experiments work is by trying to look really far away into outer space in order to measure the actual speed of the expansion of the universe. And by doing this, we're hoping to understand what exactly is causing this and what exactly is going on. But in terms of the actual explanations for, I guess, a potential particle or whatever else is causing all of this, there are just not a lot of explanations. For example, in most astrophysics textbooks, or I guess even most sciences today, will actually say that it's just part of the equation, it's just part of mathematics. Nothing is causing this except for the universe itself. But this particular explanation does not really satisfy everyone. As a matter of fact, one of the biggest and to some extent most well accepted explanations, something you can read about in some of the papers in the description below, is this unusual particle that the scientists refer to as the chameleon particle. And it's called chameleon because of its ability to sort of blend in to various types of environments. Or to be more exact, they're sort of able to change their mass and even probably other properties based on the amount of mass present around them, based on the total density. And so if they're located inside a high density area, such as for example inside some sort of a planet, even though their mass is going to become really large, they're not going to be producing a lot of force. They're only going to be pulling things apart at a really small radius of about 1 millimeter. Yet if these particles reach low density areas, so basically somewhere in between galaxies, somewhere in between galactic clusters, their mass will suddenly decrease dramatically, but at the same time they suddenly acquire an ability to influence objects really far away. Which basically means that they change depending on the location where you find them. And so to try to explain this, the scientists once again focused on the Sun, but in this case a specific area of the Sun known as the tachocline. Tachocline refers to the area you see right here in the illustration, and it's a kind of a transition area between the radiative zone and the convective zone where a lot of things mix in the star. This particular region is usually present in most stars that are more massive than about 0.3 masses of the Sun, but not in the smaller red dwarfs. And this particular layer is formed because these two zones have slightly different properties. The internal radiative zone sort of spins as a kind of a solid body. This is mostly due to the amount of pressure present inside the star. But the outer region moves more like a fluid, and because of this there is a kind of a friction or a kind of a shear created between these layers, which the scientists believe is also responsible for creating tremendously powerful magnetic fields in the Sun itself. And so tachocline is very likely an extremely magnetically charged area with a lot of other extreme effects as well. And so in this case the scientists wanted to see, so what would happen if a hypothetical chameleon particle passed through this particular region and interacted with the extremely powerful magnetic fields present in the tachocline of our Sun. And it looks like, according to the scientists, mathematically it's definitely possible. It looks like if a dark energy particle was present in this highly magnetic area, and then essentially interacted with the powerful magnetic field present in the tachocline, it would sort of get coupled with the dark energy particle, with the chameleon particle, and would produce what the scientists refer to as the dark energy quanta, which would then travel toward planet Earth and would then interact with xenon, producing the observations with the exact properties detected in the Xenon 1T experiment. Or in other words, they believe that the dark energy particles inside the Sun very likely were responsible for the 53 extra detections that we've discussed last year. Now this by itself right now is a really exciting study and also a really exciting proposition. Mostly because it suggests that we can use these unusual xenon-based detectors to not just look for potential dark matter, but to also look for dark energy, or at least one particle possibly responsible for the effects of dark energy. Although that's of course assuming that those original detections from 2016 to 2018 were not a fluke. For all we know, it could still be explained using something entirely different, possibly even some sort of interaction we never really considered. So for now we don't really know what exactly was discovered, but as of today, the mathematical model explaining dark energy as opposed to the axions that represent dark matter seems to make a little bit more sense. Hello wonderful person, this is Anton, and this right here is Albert Michelson. This was the first American to win a Nobel Prize in Science approximately 100 years ago, and it's also the person that officially stated that there was nothing else to discover in physics. We understood the world perfectly, and there were just some minor things we didn't really get yet. Well, fast forward 100 years, and it's mystery after mystery after mystery. And today we're going to talk about another such unusual mystery that has now been maybe clarified just a little bit, but we're going to talk about something we don't really understand: dark energy. Now, it only took a few decades after Michelson's statement for these scientists to realize, well, first of all, that universe was not really how we thought it was to begin with. First of all, back then people didn't even know galaxies existed. They literally believed that we just lived in one galaxy and everything we saw was part of that galaxy. It wasn't until 1930s that we realized that those little nebula that we're looking at, they're not nebula, they're actually galaxies far, far, far away from us. And our understanding of the size of the universe since has increased by a huge margin. Now, today we know that the universe also expands. This was something that Edwin Hubble was able to show relatively easily. And we also know that the universe doesn't just expand, it seems to be accelerating its expansion. And this acceleration is really difficult to explain. And for this reason, the scientists proposed the idea of dark energy. Today we think about 73% of everything in the universe is dark energy, with only about 4.6% being composed of things that are common to us, basically atoms. These scientists normally refer to this as baryonic matter. And for the most part, we also think that dark energy amount has changed over time, with some scientists believing that there was maybe no dark matter in the beginning of the universe after the Big Bang. It somehow appeared, or it's something that may have resulted from the interaction with the empty space. In other words, when it comes to mysteries, dark energy is it. It's as mysterious and as not understood as it can get. And so this is why when it comes to scientific studies, it's very exciting to see new attempts to try to understand this unusual phenomenon. So this paper right here does just that. They're trying to investigate dark energy, but not by looking at what it is, but instead by looking at what it's probably not. And they do a really good job at establishing what dark energy is not. And by the way, the idea of dark energy and also the idea of dark matter, despite both having dark in them, have nothing to do with each other. They, in a sense, have an almost opposite effect, and really the only reason we're calling them dark is because we just don't know things about them. While dark matter, we believe, is this unusual force that's responsible for keeping things together and for keeping galaxies from falling apart, somehow, the dark energy is this unusual force that seems to be forcing things apart, especially on really large-scale distances. So back in the 90s, the scientists discovered that for some unknown reason, the universe was accelerating its expansion the farther away you went. So if we were to look at the universe as it is, let's just say about 12 billion light years away from us, it would be accelerating a lot faster than we initially thought. And these scientists actually won the Nobel Prize back in 2011 for this discovery. But the idea here is that this suggested to us that something was forcing the galaxy apart from each other. And relatively recently, we even came to a conclusion that it's quite possible that the end of the universe is going to be because the universe literally rips itself apart because of the excess of dark energy in it. This is something we're still investigating, but it's sort of hard to imagine. Basically, imagine things being so far apart from each other that the universe just rips. I've made a video about this and you can actually check it out somewhere above my head, but the idea of a big rip is a little bit hard to imagine. So anyway, what exactly did the scientists do in this particular paper? And to begin explaining this, let's remind ourselves that we believe that there are four major forces in the universe. We have the strong nuclear force, we have the electromagnetic force, weak nuclear force, and the gravitational force. Two of these, gravitation and electromagnetism, are quite familiar to us because we experience them in daily lives. The other two are more nuclear and are really small in scale, so it's something we can't really imagine, but you might remember hearing about them from high school. But some scientists today believe that there is another force, the fifth force, the dark energy force. Something that happens when there is nothing around. Basically something that happens away from mass, away from galaxies, away from everything, in the middle of empty space of the universe. And so, is this fifth force responsible for expanding the universe? Is this something that we need to investigate and try to understand? Well, this is exactly what the scientists in this paper decided to do. They wanted to see if it's possible for this fifth force to exist. But just a side note, the name fifth force has also been applied to dark matter. So technically we have this fifth force and sixth force that we're investigating. We just haven't found any evidence for this yet, and so this is why we still are stuck with four forces. And the reasoning behind this paper is actually relatively simple. So if it's a force, it's a repelling force that's causing things to fly apart from each other. And so it's very likely that this fifth force would be weakest around objects with less gravity. So here, in the emptiness of space away from this galaxy, the fifth force would be the strongest. Whereas the closer to the central mass we get, the weaker this force gets, with the weakest effects being detected around really massive objects such as, for example, black holes. And so to investigate all of this, all the scientists did was create a vacuum chamber and then put two objects in there. One of them would have more mass than the other, and the object with the least mass was a simple atom of rubidium, while the larger object was some sort of a marble that they were able to move around that was also designed so that it wouldn't really create any disturbances. The overall experiment sort of looked like this, and you can find out more about this in the paper in the description below, but they used several very well-known physical principles to try to see if the larger, more massive object would have less potential dark energy than a much smaller object, which would be the little atom of rubidium-87. And they tried to simulate all of this by taking the marble, moving it around, and seeing if the effects of, well, very tiny effects of dark energy would either increase or decrease the potential repulsion effect of dark energy coming from the atom, and could then be somehow detected. Now, they've used a very well-known technique known as atom interferometry for this, where we essentially use the property of atoms to be able to act like waves or particles. And so by studying the acceleration of atoms caused by the potential dark energy, and by seeing the observed versus predicted results, they were able to establish that, well, there seems to be no effect whatsoever. In other words, The less massive body in this case was not really producing any dark energy and was not causing any more additional repulsion. So basically, no dark energy. It's not a fifth force. Or at least it's not a force that's being formed around the objects with less gravitational attraction. Because if there was a fifth force in action here, the atoms as they were moving close to the marble would actually veer off the path and produce the observation that would suggest something repulsed them, something moved them away. And this also in a sense disproves several ideas, including the so-called symmetron and chameleon theories that depend on the fifth force being dark energy. And these theories are sort of beyond the scope of this video, but the idea is that they believe that the universe is the way it is because of this unusual force. Now, I'm sure there will be follow-up studies and most likely other discussions on whether this experiment was actually well designed or not, but so far it seems that whatever dark energy is, it's not this innate force of nature. It's not something that's formed in the middle of empty space. It's something else. Maybe a particle, maybe our misunderstanding of how a universe acts and how it's shaped, or maybe something completely different. But going back to the original beginning of this video, despite being the first Science Nobel Prize winner in the US, Albert Michelson was way off in his assumption that we knew everything about the universe. It's actually pretty safe to say that we know so little about the universe today compared to what we knew 100 years ago that there are a lot more mysteries out there than there are actual pieces of knowledge we understand for certain. Hello wonderful person, this is Anton, and today we're going to be talking about dark matter and the potential collisions of this matter with planet Earth. And more specifically, we're going to be investigating potential craters created on the planet Earth that could have been produced by the mysterious dark matter. All of which is based on the upcoming study that investigates one of the craters that has very unusual origins. In the last few months, several different papers and also several different pictures confirmed the existence of dark matter even further. The more recent analysis was actually focusing on the so-called lensing effects, and several papers were able to show that the only way to produce these lensing effects the way that we see them is if there's unusual chunks of matter somewhere out there in the universe. But because there are no actual chunks of matter visible in those pictures, the only explanation here is of course the mysterious dark matter. In other words, this unusual presence, unusual mass that seems to be all over the universe. But obviously, even today we have no idea what it is, what it's made out of, but there are quite a lot of theories investigating different potential detections and also origins of this mysterious matter. Some of these theories involve all kinds of exotic particles. But this particular theory that I wanted to take a look at today focuses on dark matter being made out of so-called strange matter, also known as strange star matter. But to try to understand all of this, let's quickly take a look at what we are made out of. Here's a typical person. Inside this person, we'll find all sorts of different cells. Inside each of these cells, we'll find all sorts of different protons and neutrons and electrons. But inside each of these protons and neutrons, we'll also find what's known as quarks, which as of today is the smallest particle we've ever discovered. Here's a summary of different types of quarks and also so-called leptons we've discovered, with pretty much most of the known matter to us consisting of this stuff right here in the left column. But you can obviously make particles out of other types of quarks, and in one of the future videos we're going to be discussing various types of exotic matter scientists have been able to create by combining different types of quarks and making these different types of, I guess you can call them atoms, that do not actually exist in nature, at least today. They might have existed long time ago when the universe was much hotter and had very different density, but today we don't really think it's possible for these particles to naturally be created. Except, of course, if they're inside the neutron star. And so at least one theory of dark matter presents the dark matter as a kind of a strange matter, consisting of equal parts of up-down quarks and also strange quarks. So essentially, instead of having something like this with two up and one down quark, these types of particles would contain a mixture of up-down and also strange and charm quarks. These so-called strangelets could even grow in size by combining with regular matter, as you see in this illustration, and could hypothetically become very large and very massive. But they can also interact with regular matter through various types of magnetic interactions and potentially even lead to relatively large explosions. Although, to be honest, a lot of scientists are still not entirely sure that the strange matter as is known, or the strangelets, can actually exist at all. But if they could exist, and if they did interact with matter on Earth, we could potentially discover their effects here by looking at different types of craters. Which also brings me to a video that was made last year, where I did discuss the idea of, well, could dark matter have killed someone, and can it actually be dangerous? And it seems like the scientists behind this paper do make a suggestion that if strange matter is dark matter, then it could be dangerous, and they even present several examples where at least one fatality might have been caused by this unusual matter. So let's discuss this. According to the scientists behind this paper, every year there's at least one report of an unusual crater being created somewhere on the planet that was not produced by a meteorite and that was not a naturally produced explosion of any kind. This right here is one such example from Nicaragua. In 2015 there was a report from ABC News right here that suggested an explosion on the beach that was not produced by any known chemical reaction. But most interestingly, in 2016 there was a fatality reported in India that did produce a crater and even injured 3 other people, but there was no report of anything being recovered, there was no chemical reaction that could have caused this, and this explosion seems to have occurred when something from space did collide with planet Earth, but nothing physical was reported to be found. And to try to figure out if this could have been caused by some kind of strange matter, the scientists behind this paper combined their simulations and their actual theory, including the simulations of what would happen if this unusual strange matter collided with matter on Earth, with the actual physical excavation and analysis of different types of rocks inside one such crater that was created in Ireland in 1985. And the crater itself was produced in 1985 and witnessed by several people walking their dogs. There was no meteorite recovered, there was nothing actually even falling to the ground, but interestingly the explosion itself created the effects that were observed very deep in the ground. In other words, the rocks and even the material underneath the rocks was affected by whatever caused this explosion. But unlike a meteorite collision, first of all, nothing was seen fall into the ground, no fragments of any kind were recovered, there was no chemical reaction involved, no residue of any explosives, and most importantly, they could not see any damage attributed to pressure of something hitting the ground from top at very high velocities, as if something just exploded but did not produce enough pressure to crush the rocks underneath. And interestingly, even the granite rocks recovered from approximately 5 meters in depth or 15 feet in depth were shattered into little pieces, and to scientists behind this paper this suggested that whatever piece of matter hit the planet that day was extremely dense and had extremely high nuclear matter density, somewhat similar to what a lot of the predictions of the so-called strange matter indicate, similar to the so-called quark matter or strange matter. But this was probably a very tiny piece, only about 10 kilograms or about 20 pounds in mass, and this would make this object extremely tiny. And though theoretically it could also obviously be a piece of, for example, neutronium matter or neutron star matter, or even a tiny black hole, when it comes to black holes we know that small black holes like this would have actually disappeared a long time ago. Their actual lifespan would only be about 150 years. And neutron star matter would not really be stable enough to travel by itself unless it's inside a neutron star. And so according to the scientists behind this paper, the only thing that could have collided with planet Earth was probably some sort of a strange matter, which they also believe is the only thing that could potentially produce all of the effects observed in this crater. And this of course presents a somewhat interesting but also somewhat scary scenario, because every year there's a report of a non-meteorite crater, and at least one such crater in India resulted in someone's death. So if all of these events are connected, and if the scientists behind this paper are onto something, then it means that we need to start taking dark matter a little bit more seriously and start investigating if it actually does pose threat to humans here on Earth. But it's very important to understand that this is just a hypothesis for now. There's really not enough proof to suggest if this is actually what happened there. There's also no proof to suggest that this is what happened in India, so a lot more investigations and a lot more analysis is needed before we can definitively say that at least once a year, chunks of dark matter do fall on the planet and create explosions large enough to potentially hurt people. On the more positive side, of course, this also creates an opportunity for us to potentially recover some of this matter one day and maybe even use it for some sort of an energy production. In other words, there is a possibility, if this is of course true, that this type of matter could create a new way for us to produce energy that could even allow us to travel across the entire universe and maybe even create technology that we can't even think of right now. Hello wonderful person, this is Anton, and today we're going to be talking about these two mysterious galaxies that a few years ago have been discovered to possess no dark matter whatsoever. The galaxies that were very difficult to explain and very difficult to try to understand using our modern understanding of physics. But following a thorough analysis using the data from the Hubble telescope, a team of astronomers was finally able to definitively answer and definitively show exactly what's happening in these galaxies, although not really answering some of the major mysteries. So let's talk a little bit more about this. First of all, let's establish the location. So this right here is our own Milky Way galaxy. If we were to look into the night skies somewhere in this direction, we would discover this other nearby galaxy, relatively nearby galaxy, known as NGC 1052. It's somewhere right there. This galaxy became particularly interesting to scientists when they discovered that it possesses an extremely powerful black hole in the middle, roughly around 150 million masses of the Sun, which is more than 30 times as massive as the one in the middle of our own galaxy. That particular black hole also seems to possess a very powerful magnetic field and is also one of the most studied black holes out there. And the distance to planet Earth from here is about 63 million light years away from us, meaning that the light we're seeing from this galaxy left this galaxy around the same time when the dinosaurs disappeared from planet Earth. But this is not really what we're talking about, because we're actually here for its neighbors. It also possesses two neighbors very close to it that should technically be somewhere in this image, but they're not really that easily visible. The galaxy itself is this one, and this is its neighbor NGC 1042. But back in 2018, two astronomers, one from Canada and one from the US, decided to use this very interesting telescopic array known as Dragonfly. And this by itself is literally just a bunch of consumer-grade cameras like this one, connected all together into a single network. And by using this, they discovered these two invisible neighbors of this galaxy. The neighbor number one, NGC 1052-DF2, which stands for Dragonfly 2, and NGC 1052-DF4, with both galaxies sort of looking like this. Now, there isn't much to see here, but this is a type of a galaxy known as the Ultra Diffuse Galaxy, or UDF for short. The thing about ultra diffuse galaxies is that, well, first of all, there are quite a lot of them out there, but they're naturally very difficult to see. Mostly because, unlike a typical galaxy that allows us to see it through the illumination of various stars in the region, a typical UDF like this one right here is going to have very low luminosity, even though in terms of size it's very comparable to the Milky Way galaxy. And interestingly enough, the majority of UDFs discovered so far also have a relatively similar mass to the Milky Way as well, which is somewhat strange because they don't seem to possess a lot of stars, but in terms of mass it's more or less equal. And that's because a lot of these UDF galaxies, with the most famous example being this one right here known as Dragonfly 44, are essentially these ultra-massive dark matter galaxies. They possess a huge amount of dark matter, but not a lot of stars on the inside. And because of this, they've been of particular interest to astronomers trying to understand what exactly dark matter is. But then, on the other side of the spectrum, and essentially to everyone's surprise, in 2018 the scientists discovered these two galaxies, DF2 and DF4, and they are literally the opposite. They essentially seem to possess absolutely no dark matter whatsoever. At least that was the initial impression the scientists got from this. But how do they know this? Well, by looking at the actual stars and actual globular clusters inside of these galaxies, they've established that the average speed of motion of different globular clusters on the inside was around 8 km per second. Even though for a normal galaxy that possesses dark matter, this speed should have been about 30 km per second. Which of course implied that something here didn't add up. Either the measurements of the speed were wrong, or possibly the distance measurements to the galaxies were wrong as well. If the galaxy was much closer to us, then the speed would also be different, and thus a lot of things could be explained that way. And that's exactly what some of the initial papers tried to do. They tried to explain this by either recalculating the distance or by recalculating the speed of globular clusters. But over time, the speed was confirmed to be 8 kilometers per second, possibly even a little bit lower. And then this one paper that came out 2 years ago established that maybe the distance was wrong after all. Here, the distance measurements suggested that it was actually connected to a completely different galaxy, approximately 40 million light-years away from us, not 60 million as previously claimed. Which would then technically explain some of the observations and would also mean that maybe there is some dark matter in this galaxy after all. But to try to confirm or to try to disprove all of this, another type of observation was needed to try to once and for all answer what's happening with these galaxies after all. And so the scientists behind a very recent paper, that as always you can find in the description below, decided to use the observations from the incredible Hubble telescope, which unfortunately at the time I'm making this video is still disabled and is unable to perform any operations anymore. The computer system in the telescope might have actually been damaged permanently. But we'll talk more about this in some of the future videos once we get some updates. Anyway, so by using Hubble, the scientists decided to focus on a slightly different data to establish the direct distance to this galaxy. They used an advanced camera for surveys on the Hubble telescope and looked at the tip of the red giant branch, also known as TRGB analysis. Now this is usually the most accurate distance analysis of the nearby galaxies. And this technique relies on our thorough understanding of a lot of stars as they age and as they develop into the red giants. Our sun is actually going to go through this stage as well, and it's specifically related to this idea of helium burning or helium flash. This is when a star becomes large enough and develops a large enough helium core on the inside that it starts burning all of this helium and creating carbon instead. This is known as the helium flash and is always present in stars between 0.8 masses of the Sun and 2 masses of the Sun, something that happens during the red giant stage of many of these stars. And because the helium flash generally produces the same amount of luminosity no matter what star it is, it becomes relatively easy for the scientists to figure out the total distance to these objects by using them as a kind of a distance candle. And so by using the Hubble telescope, they zoomed in to several locations in this particular galaxy, and thus were able to study some of the helium flash in some of the stars present in this galaxy, allowing them to determine the exact distance to those stars. And to their surprise, the distance was even farther. It was roughly around 72 million light-years away from us, which literally means that this galaxy very likely possesses no dark matter whatsoever. And because they've used a very similar observation on the other galaxy, DF4, and found something very similar there as well, it only seems to reinforce the original discovery even more. These two galaxies, for some reason, do not seem to possess any dark matter whatsoever, no matter what it actually is, because nobody really knows what it is just yet. Although, quick correction, the word dark matter by itself is a very bad name for this. It's a phenomenon, it's not really necessarily matter of any kind, it's just something we don't really understand just yet. As I've previously mentioned in one of the previous videos, a much better term for this would be unidentified mass phenomenon, because that's basically what it is. It's something that seems to keep galaxies together, but it's not necessarily any kind of a particle or a mass. Nobody really knows what it is just yet. But how these galaxies are formed and what exactly stripped them of dark matter, that's of course another question for another day. Although there was another study not so long ago that might have discovered that it was actually a result of what's known as the tidal stripping from a relatively large and relatively massive neighbor and might have actually just stolen some of the matter from inside these galaxies, with some of the hints being present inside these very large and somewhat difficult to see galactic streams that are usually formed when galaxies strip one another of matter. And this of course means that these galaxies were probably much smaller in size before, much more compact, and the stars on the inside were also orbiting much faster. But as the dark matter was taken out of them, the stars sort of started to spread apart, created the ultra-diffuse galaxies, which also lowered their velocity over time. That's one of the explanations so far. But here's another question. Does the presence of these galaxies and the fact that they have no dark matter automatically prove the existence of dark matter? Does it mean that, for example, other ideas like MOND or modified Newtonian dynamics is proven completely wrong by the presence of these galaxies? Well, some of the studies already implied this, but in this particular study, the scientists kind of give these ideas one last chance. One of the unusual parameters in the MOND is something that's known as the external field effect. It's something we'll maybe discuss in one of the future videos, but it essentially implies that a massive galaxy can hypothetically have a very unusual effect on its dwarf neighbors. It can basically slow down some of the rotation of stars in those galaxies. And hypothetically speaking, it would be possible for both DF2 and of course DF4 galaxies to have the observed velocities if they are located at just the right distance from a massive galaxy. And so in this case, if there is an equal distance between these two galaxies and these two galaxies, and they also have relatively similar masses, to some extent MON can actually explain what we're observing as well. But the scientists do mention that the chance of this being the fact, and also the chance that these two galaxies are exactly the same distance and there's exactly the same mass present here, currently at least, is extremely low. So it's not really disproving these theories completely, but it's not really helping them either. Which of course once again means that at the moment at least, the idea of dark matter being the real thing and just not being present in here is currently the best possible explanation. And also by discovering similar galaxies somewhere else out there, and possibly figuring out what exactly happened to them, might help us once and for all answer the question of the mystery of this unusual dark matter phenomenon after all. If it exists, what exactly it is? If it doesn't exist, what exactly is happening there to begin with? For now though, it's a very interesting discovery, very interesting confirmation, and definitely an extremely interesting analysis of the mystery of two galaxies the scientists couldn't agree on for about 3 years now. Although at least for now, it looks like it's been finally settled. There doesn't seem to be any dark matter or any presence of anything related to dark matter in these galaxies, and their distance is definitely farther away than we initially thought. But even though this is a pretty cool discovery and really cool analysis, chances are we're going to be discovering even more of these galaxies in the next few years. The scientists using this telescope are giving it a huge upgrade, most likely making it 120 lenses from the 48 currently present there, which means that it's going to have a lot more power to find even more of these galaxies somewhere out there. Once in a while, scientists discover something really incredible about our own galaxy, something that helps us understand how things here operate and how things move around. And sometimes these new discoveries help us answer questions that we couldn't really answer before. Hello wonderful person, today we're going to be talking about one such discovery. A discovery that connects one of the features in our galaxies with one of the mysterious stellar streams that has been traveling around the galaxy in the last few billion years, the stream known as the Hercules stream. And what this discovery potentially suggests is that something mysterious, very likely dark matter, which we don't really understand very well just yet, is causing the galaxy to slow down over time and is also causing some of the stars to leave to the outskirts. Which is actually something that a lot of different theories predicted before, but has never really been proved observationally. And so now we have this proof. But first of all, well, let's start in the middle of our own galaxy. If we look at the Milky Way from, I guess, the top in this case, we would actually discover a shape known as the bar, specifically a galactic bar. It's not very easy to see at first, and it's also very difficult to see in all galaxies, but it very likely looks something like this from the top. We're located somewhere right here, and the bar itself is sort of going across this way. And it also connects to the two major arms of our galaxy. Now this is of course a pure speculation at the moment because we can't really see the galaxy from the top, but it's based on the investigations of star motion and also is based on pictures of other similar spiral galaxies we have from the outside. For example, this is NGC 1300 with an extremely beautiful galactic bar you can see right here. And there are quite a lot of other examples, such as NGC 4921, NGC 1073, or this right here, NGC 1365. As a matter of fact, about 2/3 of all spiral galaxies seem to have these bars, and the scientists have even established that it's a feature that seems to appear in older, more established galaxies. And so, for example, when the scientists look at some of the ancient galaxies in distant universe, only about 20% of all of them will contain bars. But when we look at more recent times, about 65% of galaxies contain them. It implies that these features established over time. Also, many of these galaxies, such as M83 right here, will also often contain a very active galactic nucleus in the middle. Or basically they'll have an active black hole producing a lot of radiation and a lot of emissions at all times. Which also of course implies that the Milky Way galaxy was such a galaxy in the past. We do have signs of this all over the place. These features also usually act as a kind of a stellar nursery, producing a lot of new stars, which then sort of travel across the galaxy and spread pretty much all over the place as well. But the actual formation process of these bars is not entirely well understood. It's something to do with the density wave coming from the center, but is still being debated even today. What's not being debated is the fact that these galactic bars play a really large role in, well, basically controlling the motions of things in a galaxy. Because this represents such a huge massive object, it will usually affect a lot of motion of stars and a lot of interstellar gas that orbits around the galaxy. And many of these stars, especially the ones right here, will often become basically locked to this bar, or essentially become gravitationally linked to it in a very similar manner to how Jupiter that you see right here will actually lock some of the asteroids gravitationally, creating what's known as centaurs. And so generally speaking, we expect a lot of stars to form a kind of a bar and to kind of spin in such a way that the bar will maintain its shape over time, billions of years actually. But all of these gravitationally linked stars, or the stars in resonance with this bar, will also start experiencing any kind of effect that the bar experiences. So for example, if suddenly this bar starts to slow down and to basically start moving a little bit slower, the resonance from the bar itself will obviously start affecting the stars as well. Another way of looking at this is to once again take a look at the Trojans of Jupiter. So if suddenly I were to take Jupiter and to slowly start decreasing its speed, which will take its orbit farther and farther away from the Sun because now it's moving a little bit slower, eventually all of these Trojans that were connected to Jupiter will also, because of the resonance, start moving to the outskirts of the solar system and assume new resonance there. Meaning that if the central bar starts slowing down, the stars that were connected to it through resonance will also start moving to the outskirts of the galaxy. At least that's what a lot of theories have predicted in the past. But how can we possibly prove this, and is there any actual evidence out there? Well, one way to prove this is to find stars that did come from the inner regions of the galaxy and that are maybe connected through resonance to the galactic bar. And it looks like we might have actually found them. So first of all, there are a lot of these galactic streams around the Milky Way galaxy. This image here sort of illustrates some of them. Now, most of them are produced through, well, basically leftovers from galactic collisions. Some of them are produced in other ways. Some of them are still mysterious. But at least one of them, called Hercules Stream, involves a bunch of stars moving across the galaxy not so far away from us, but with a relatively similar speed to each other, however a speed that's different from everything else around them. All of these stars in a Hercules stream are moving about 40 kilometers per second slower than the stars near them. Okay, so for example, if we look at this picture and we look at our own Sun, we know that the Sun is moving around the galaxy at a relative speed of about 230 kilometers per second. But these stars in the Hercules stream are moving slower. So here, I guess it would be about 190 kilometers per second. And for the most part, they all sort of connected to one another. But it just so happens that the scientists behind the recent paper discovered that they're also connected to something else. And you probably guessed what it is. They're all connected to the central galactic bar of the Milky Way galaxy. They're basically moving in resonance with the galactic bar, which kind of implies that they probably came from the galactic bar a long time ago. But that's just the first piece of evidence. These scientists then also compared the metallicity of these stars, or basically how much of various materials they have on the inside, with the overall metallicity of other stars in the center of the galaxy compared to the stars near us. Now, generally when it comes to metallicity, in some of the past studies, the scientists have discovered that there is actually a kind of a gradient in a typical galaxy, including of course the Milky Way. And so generally speaking, as you move away from the center of the galaxy, the average metallicity of the stars will decrease. Whereas if you move within the approximately 10 to 15,000 light years away from the center, the metallicity there will start increasing. And the closer to the center you get, the more metallicity we can sort of expect. With some obvious exceptions, including things like, for example, globular clusters, which will usually have low metallicity. But the general idea here is that by looking at the average metallicity of stars in, for example, a typical cluster, or in this case, a galactic stream, such as the Hercules stream, we can then sort of figure out what part of the galaxy this stream or these stars might have come from. For example, if we find a star that's very similar in metallicity to our Sun, it probably came from the region around here, about 25,000 light years away from the center of the galaxy. If we find something much lower in metallicity, it probably came from slightly farther away. If it's something higher in metallicity, it probably came from a little bit closer to the center. Well, it turns out that the metallicity of the stars in the Hercules stream do suggest that they actually came from much deeper inside the galaxy, or in other words, that they actually traveled to the outskirts. And so the motion of the stars from inside the galaxy to the outside, plus the fact that they're connected gravitationally through resonance with the galactic bar, both of these facts do suggest that, well, the galactic bar very likely slowed down over time. As a matter of fact, the calculations suggest that it slowed down by about 24% since the original creation, which also means that the galaxy sort of slowed down its rotation as well. It spins about 24 times slower now than it used to spin in the beginning. And theoretically speaking, there is really only one explanation to how this is possible. It's only possible if our galaxy is literally inside some sort of a large galactic halo of dark matter. Something very massive, something very invisible, something that makes our galaxy slowly slow down. Basically slowly slowing things down as the things spin inside of it. And unfortunately, that's not really good news for alternative theories. If this is true, if the galaxy indeed slowed down, there is really no other explanation available to us. No other theory provides enough answers to show us how a galaxy can slow down so quickly over time. But the theories invoking dark matter explaining the universe explain all of this really well. As a matter of fact, they provide a very direct evidence that something is definitely slowing down the galaxy, and that something is massive enough to also explain a lot of other observations. That massive thing, phenomenon, whatever you want to call it, is dark matter. Although nobody still knows what exactly it is, we just seem to be observing the effects, not really the actual, I guess, particle or whatever it is responsible for the effects. Which is why I generally prefer to call this anomalous mass phenomenon. It's some sort of a mass, it's some sort of anomaly, and it's a thing, it's an event, it's a phenomenon, but possibly not a particle. But still, a really cool study, amazing evidence, and most importantly, provides a lot of evidence for a lot of mysteries, including the mysteries of the Hercules stream, and helps us understand how the actual galactic bars transform over time. Hello wonderful person, this is Anton, and in this video we're going to be talking about the mystery of dark matter. But more specifically, we're going to talk and look at a paper that discusses the death from dark matter. In other words, it tries to investigate why is it that it seems that nobody has ever died from dark matter. And I guess we really should start with the fact that we still have no idea what dark matter really is. We only see the effects of dark matter by looking at the galactic speeds and how stars in various galaxies move. And we also see the effects of gravitational lensing when looking at distant objects, because some of them seem to have been sort of shifted and twisted by very dense gravitational attractors. But other than that, we don't really know what it is. For the longest time, the scientists used these really large, really expensive detectors, like this one right here. This is in South Korea, made in collaboration with Yale University, and they've spent billions and billions of dollars to try to discover these particles they refer to as WIMPs, also known as weakly interacting massive particles. So we haven't found anything. We don't really know how exactly dark matter works or what it's made out of. But some scientists started to speculate maybe we can learn more about it by looking at what we know as a fact. And the fact is that many different space phenomena out there have somehow affected human life, or maybe even endangered human life, sometimes almost killing humans. Like for example, various space debris that we know constantly re-enters our planet, in at least one instance back in 1997 almost killed a person. This lady right here, Lottie Williams, who is seen in this picture holding this part of a launch of a rocket that basically almost hit her on the head, but luckily missed and hit her on the shoulder. And so to try to understand what dark matter might be, several scientists tried to write papers on what could potentially happen if dark matter killed a person. At least one paper back in 2012 investigated this in a little bit more detail to try to discover so what would really happen to human body if WIMPs basically hit through it, and what sort of interaction would WIMPs have with humans. And so what they discovered is that a typical human body would receive roughly around 10 WIMP collisions per year, with the most extreme sort of calculation of being 1 WIMP per minute. In other words, you would get hit with one little particle of dark matter every single minute. And this would result in something equivalent to background radiation that we all get right now from things like cosmic radiation, from things like radon, that's the gas all over the place on our planet. And it would be completely minuscule in comparison. In other words, you would not really feel any effect whatsoever. So for these WIMPs to kill human beings would be quite impossible. And so they kind of abandoned this idea, but then we had another new study that suggested that maybe dark matter is not made out of WIMPs. Maybe it's made of something called macro. Macro dark matter is kind of this new thing that's going on in science, where scientists realize that you can actually create bigger particles out of the same quarks and the same subatomic particles that make up regular matter, but it just so happens that you can make really large particles. And today scientists refer to this as macro dark matter. The paper from 2014 is in the description below if you want to learn a little bit more about it. But the idea here is pretty simple. You can hypothetically create particles that are extremely large in size. Some of them could be as big as, let's say, a golf ball. And they believe that it's possible that dark matter might be made of these unusual particles. And so the very recent paper that was released only a few weeks ago from when I'm making this video investigates this. They decided to approach this from the macro dark matter perspective, and they decided to find out what would happen to human body if suddenly you were hit by this macro dark matter coming out of outer space and hitting your body. Well, the calculation suggests that with certain types of macro dark matter, it would literally be equivalent to being hit by, well, what you see on the screen, a lightsaber. They compare it to this tremendously powerful, tremendously hot plasma cylinder that would pierce your body so fast and with so much power that there would be a hole in your body for no apparent reason. And this is of course interesting because nobody has ever been reported to die from this. And this paper is kind of speculative, very hypothetical, but creates a very important limit for what macro dark matter could be. It means that it cannot be certain things that would have killed many human beings around the planet. It means that it cannot be a certain mass or a certain size and has to be a lot different. Because if it wasn't, a lot of people would have been already dead from these unusual, mysterious lightsaber strikes across the planet. And one of the reasons why dark matter could even do this to a human body is because it's not really affected by matter as much, but it does have energy in it, and as it passes through different objects, it would leave behind these really powerful bullet-like streaks of plasma that's roughly around 10 million degrees Celsius. So it would still have an effect, but it would just not really interact with the matter. And so by doing various calculations, the scientists behind this paper discovered that, well, there's definitely has to be a limit of size and mass for these macros, because otherwise we would see fatalities from dark matter everywhere. And they discovered that it has to be smaller than a micron, which is roughly around this big. Here's a micron compared to human hair. And it has to be less heavy or lighter than roughly around 50 kilograms or about 110 pounds. So in other words, these macros cannot really be heavier or bigger than that because they would create these very fatal collisions. We would see these collisions everywhere, and it's very likely that a lot of people would be dead around the world from the collisions with macro dark matter. And even though this paper is very hypothetical, it's a really good start for how we can sort of pin down to what dark matter could be and then start looking for it. Because currently all of the dark matter detectors are only looking for WIMPs. None of them are looking for this macro dark matter, and we don't really even know what to look for. If it is a macro dark matter, how big does it have to be? How massive does it have to be? And so by looking around our planet and also by looking at essentially the effects of this hypothetical dark matter, we might be able to pin down the sizes and also the masses involved and then be able to detect it in more detail. Now, how exactly are we going to do this? Well, the paper suggests using people, but also using granite rocks. In other words, by looking around various rock formations, we might be able to see the actual marks from this superheated plasma that could then be used to track down the size and the mass of dark matter. But like I said, it's still really early in its discussion, and according to these scientists, they've only looked around the rocks in the vicinity of their university. They haven't even looked beyond or tried to analyze this in more sort of experimental and scientific way. Nevertheless though, if one day we discover an unusual lightsaber-like mark in a rock or in a person, we know that we may have discovered the elusive dark matter. Hello wonderful person, this is Anton, and today we're going to be talking about another theory that tries to explain the potential origin of the mysterious dark matter. Where did it come from and what exactly is it made out of? And in this case, we're going to be focusing on this very theoretical concept that proposes that the dark matter might actually, after all, be made out of tiny black holes. Although in this case, the scientists behind the paper you can find in the description propose a relatively complex explanation involving a lot of particle physics and a lot of ideas from the changes in the early universe. But I figured it's still a pretty cool explanation, still a pretty good idea, pretty solid idea, and it's definitely something that I could try to explain in this video. And so the title of this paper is Primordial Black Holes from a Cosmic Phase Transition, the Collapse of Fermi Balls. And it tries to explain the mysterious dark matter as what's known as primordial black holes that existed since the beginning of the universe. Now first, quick side note, we still obviously have no idea what dark matter really is. We obviously see the effects of the mysterious dark matter, such as the expected versus observed rotation curves of various galaxies, along with some unexpected lensing effects from the invisible mass in the middle of different clusters that shouldn't really be there, with a lot of other observations we've discussed in some of the previous videos. But the problem here is that, well, for the past few decades, despite many different experiments, no particle has been discovered to try to explain all of this. For example, one of the most common theories uses what's known as WIMPs, weakly interactive massive particles, and this is supposed to be the explanation for how dark matter works, with the other common explanation being another particle known as Axion. But though theoretically they do make sense, none of the experiments so far have found anything. No WIMPs or Axions have been found, despite many different attempts to find them. And naturally, because of this, there are several alternative explanations to dark matter. The most popular, or I guess the most famous one, is known as MOND. But they don't explain everything. As a matter of fact, some things they cannot explain at all, and because of this, not everyone, or actually most scientists, do not accept them. The dark matter still is believed to be some sort of a particle, or maybe a tiny black hole. As a matter of fact, Stephen Hawking himself always believed that it was primordial black holes. Now there's a video from a couple of years ago where the Japanese scientists tried to investigate this idea, and they did so in a very clever way. They wanted to see if there are really these primordial black holes, or at least some sorts of black holes, traveling across the Andromeda Galaxy. And so they looked at the Andromeda Galaxy for a long period of time, and they tried to discover any kind of signs of these primordial black holes by looking at the gravitational lensing effects of various invisible dense objects moving in front of different stars. Now they've only found one, even though they expected thousands, and this implied to them that there were no massive black holes, or at least black holes in the range of the mass of our Sun, or possibly a few masses of Jupiter, traveling in the Andromeda Galaxy. Which also implied that the larger black holes could not explain dark matter. And normal black holes, the so-called stellar black holes, definitely cannot explain anything. You would have to have a lot of them everywhere, and we'll be able to see them in many different surveys we've already conducted. As a matter of fact, just in terms of the numbers of the stars in the galaxy, there are just not enough stars to produce all of these black holes. Nevertheless, primordial black holes could be entirely different. They would not be produced in the same way. They could be produced in an entirely different way, and they could also be a lot less massive and thus invisible, or at least somewhat invisible. And because of this, in that paper from the Japanese scientists, they also established that if there are primordial black holes, they have to be less than a mass of the moon or so, or possibly a mass of several asteroids. But I guess the question is, well, how would they be produced and what exactly could create such black holes? Well, there have been many propositions, but the one in this particular paper is particularly intriguing. And the explanation here involves what happened in the universe in the first moments after the Big Bang started. Essentially, the universe before a lot of particles became particles, before the fundamental forces solidified and became the forces we know today, and essentially when things were extremely different, the universe was extremely hot, and everything was extremely dense, extremely hot, and somewhat difficult to imagine. But we know that this probably existed in the first few moments, simply based on the observations from the CMB, the cosmic microwave background. And during that time there were a lot of different transitions and changes of state, as it's known. Essentially, as the universe cooled down, things changed into other things. And these changes of state can be sort of compared to how liquid water turns into ice, or how liquid water turns into gas. But in this case, today the physicists believe that the entire universe can be described in terms of different scalar fields. Fields of energy, fields of forces, and in each of those fields, various particles are produced through the breaking of symmetry. So essentially, in order to get a photon, or in order to get any particle, you would have to have certain field suddenly have some sort of a breaking of symmetry in order for the particle to be formed. Now, in this case, the scientists also are pretty certain that these fields transformed in their state, especially when the universe started to cool down. And during that transformation, it's very likely that some of the particles that used to be present in these fields might have also been somehow affected. And so this so-called phase transition is essentially what forms the idea behind this paper. They believe that the phase transition might have resulted in the formation of these primordial black holes. Here's how they kind of explain this. And so let's use an analogy here. The scalar field is going to be liquid water, or just an ocean in a sense. And in this case, our ocean is going to have its own particles that would not exist in modern universe. We're going to think of these particles as the tiny crystals of salt that are present everywhere in every ocean on the planet. And so we have the liquid ocean and we have the salt. Now normally on Earth, as the temperature increases, water turns into gas. But in this case, we're actually cooling down the universe, so it's slightly different. Anyway, as the universe was cooling down, a lot of these fields started to transition their state. They started to experience phase transition. And so in this case, the liquid water is going to be turning into gas. It's going to start evaporating. But just like with water, it doesn't just suddenly happen everywhere. When you boil water, it doesn't just entirely evaporate right away. It starts with tiny bubbles, and these bubbles start to kind of spread slowly, moving from one place to another, eventually combining, growing in size, and turning liquid water into water gas. But in our ocean water, what happens to the salt? The salt particles will actually start accumulating and creating tiny crystals. At least that's what happens if you try to evaporate salt water, and these crystals sometimes grow in size and become bigger and bigger. And once all of the water is gone, you get something like this. And so something similar might have happened according to the scientists in this paper. They believe that in the early universe there were these unusual particles, probably some sort of a fermion particles, fermions referring to particles that don't really like to be in the same place and tend to repel each other. So for example, electrons, protons, neutrons, they're all fermions. And as these scalar fields in our early universe started to transition, the early fermions very likely could not transition with them. They most likely just started to kind of clump together and create bigger and bigger lumps, with everything around them slowly transitioning into the state where they could not exist. So something similar actually does happen in salt water when you start evaporating it and when the salt starts to deposit on the bottom. And as the scalar field started to transition, the leftover fermions started to form what the scientists refer to as Fermi balls. And this is an actual concept that was proposed back in 1994 that some scientists do believe might exist in certain conditions. So in this case, a Fermi ball is a collection of fermions that should really not be together because of their repulsion force, but in some cases, through what's known as the Yukawa interaction, they can actually collect into larger pieces. The pieces would be the Fermi balls, and as these Fermi balls grow larger and larger, at some point they can reach a threshold where they basically collapse, simply because they could no longer support themselves. That's literally how black holes form as well. And as a result, from these Fermi balls, we get these primordial black holes. And that's sort of how the origin of these black holes is explained in the paper. They also provide a somewhat basic illustration showing us how all of this works. So as these bubbles grow larger and larger, they kind of start to separate a lot of these fermions into the only areas where they can still exist. And eventually, as the universe starts to transition through its phase, we're left with these regions that they refer to as Fermi balls with quite a lot of mass on the inside, which then end up collapsing, producing primordial black holes, with black holes being able to exist in that transition phase of the scalar field. And so essentially, in their theory, the formation of the primordial black holes depends on two principles. First is the transition of the scalar field in the early universe, something that we know existed for sure. But the second part here is a little bit more hypothetical. Here the expectation is that something else existed in the early universe, some other types of fermions that do not exist today, and that something then started to bunch into Fermi balls, which then collapsed into black holes. Now, the only way for us to ever try to prove any of this is to maybe somehow try to recreate this early universe in the lab. But the thing is, that will be pretty difficult, almost impossible. This would require way more energy than we can actually produce right now. And so for now, this is just a theoretical explanation. The only other way to try to prove this is to maybe find one of these primordial black holes. So in this case, the scientists do actually make a speculation about the mass and potential size of these black holes. Their calculations suggest that the mass of a typical primordial black hole could be about 10 to the power of 14 kilograms, equivalent to the total mass of carbon fixed by photosynthesis on Earth every single year, or approximately 10 times the mass of the famous 67P Churyumov-Gerasimenko comet, which would be equivalent to a mass of an asteroid that's approximately 3 kilometers in diameter. But I guess the question is, well, can these black holes exist? Remember, black holes also evaporate. That's of course based on the Stephen Hawking's prediction of what we refer to as the Hawking radiation. And black holes that are not very massive are going to disappear pretty quickly. And so I guess the question is, how long can a black hole of this mass exist in the universe? And there's actually a really easy way to calculate this. There are a lot of different calculators online, but I found this one by Victor Toth to be one of the most accurate ones. And here, if you enter the mass of the black hole, it tells you pretty much everything about it, including the potential lifetime. And so if we enter the mass that's proposed in the paper, we'll discover that this particular black hole can actually survive for a pretty long time. That's approximately 100 million times longer than the current age of the universe. And so these black holes are going to be around for a long time, assuming they exist. Now, can we find out if they exist? That's the other question. Currently, there's really no way for us to determine if they are real and if they actually are out there. But some of the future telescopes will definitely allow us to study what's known as the microlensing effects. In this case, extremely fast microlensing effects. The effects produced by these very small bodies, extremely dense bodies, passing in front of distant stars. And if by some chance we start detecting a lot of these microlensing effects all over the place, especially from objects that seem to be asteroids but are not really visible in any other way, in that particular case, there might be a chance to discover some of these primordial black holes. Although at the moment, it's still really far to tell if we'll ever be able to find them. But since they represent approximately 80% of all of the mass in the universe, well, they should be pretty much everywhere around us, and we should be able to find them possibly even in our own solar system. And so in that sense, this is actually something really exciting. If one day we start discovering unusual emissions of different X-rays and possibly even gamma rays coming from some sort of a not so distant object in the solar system, in that case, that would definitely be some sort of a primordial black hole. But since it would be extremely small in size, chances are this particular black hole would not really be producing that much radiation and would still be somewhat invisible. These objects would be 1,000 or several thousand times smaller than a typical virus. And that means that it would still be extremely challenging to find them and to actually prove their existence. Nevertheless, it's still an interesting theory, an interesting proposition, and a theory that's been proposed many times with different explanations before. So it's not something that scientists do not think exists. As a matter of fact, primordial black holes are an explanation for a lot of different phenomena, including supermassive black holes. And so their existence is almost certain. But how small they get and also their numbers is of course a completely different question, something that we cannot currently answer. Hello wonderful person, this is Anton, and today we're going to be talking about this very interesting study that might have identified clues of the mysterious Axions, the particles that were predicted several decades ago and that might also help us explain a lot of things in the universe, including the mystery of dark matter. And although the results themselves are not really verified by other studies yet, and might also have some other explanations, it's still a very interesting study and a very interesting discovery. So let's discuss this in more detail, starting with axions? What are axions? Like so many other things in physics, this one actually starts with an unresolved mystery or unresolved problem in particle physics. And the idea here is behind what's known as symmetry. Now, symmetry is basically just a mirror image of something. The best example here would be the symmetry observed in electrons and their antiparticles known as positrons. For example, if an electron and a positron are created, they'll usually have what's known as the parity symmetry. One will be left-handed, one will be right-handed. Then we have another type of symmetry for electrons and for anything with electromagnetic force. And that's called charge symmetry, where a positron will have a positive charge and an electron will have a negative charge. And together they create what's known as CP symmetry, which is in essence the electron and the positron. And this is something that does actually make sense, but a lot of physicists early on assumed that this is true of any kind of a particle and antiparticle. In other words, a lot of scientists initially assumed that, for example, if we were to take a proton and an antiproton, you would have a very similar sort of situation where you have two symmetrical particles. But as I mentioned in one of the previous videos, at some point we discovered that the weak force doesn't have this symmetry. For some reason, the weak force has what's known as CP violation. And this of course eventually led to the Nobel Prize and a lot of really interesting propositions, and basically there's a whole video about it. But what's even more unusual is that because of this proposition, it was also assumed that there should be a similar type of a CP violation when it comes to other forces and other particles. And by the way, you can read more about this CP violation and a lot of these ideas in the blog post I'm posting in the description below, written by this wonderful person who also created the images I just used. And anyway, long story short, it was assumed that CP violation would be also true of anything related to the strong force. In other words, the scientists believed that maybe only electromagnetic force, only electrons and positrons would be symmetric, where everything else would be not symmetric. But it turns out, for some reason, the strong force, or the strongest of the fundamental forces, is symmetrical after all. But theoretically and mathematically, no one can actually explain it. And today this is known as the strong CP problem, and it's essentially one of the biggest mysteries, unsolved mysteries in physics, and is one of the major problems that no one can explain. But one of the explanations, or at least one of the more likely propositions, was this right here. I'm going to assume that it's pronounced Paxay Quinn theory, but because I've never met those people, I don't really know how they pronounce their names. So my apologies if you're watching this. Anyway, long story short again, to try to explain this symmetry problem, the scientists here proposed that, well, you can actually explain everything if there is a hypothetical particle that's produced when the strong force interactions happen. Now, in particle physics, that's often the explanation for a lot of things, a new particle, and in many cases, this has been kind of proven. For example, the so-called Higgs boson that was discovered not so long ago was one of these hypothetical particles that were proposed a long time ago. And so here, to explain the symmetrical properties of certain quarks and antiquarks and certain other particles, the scientists proposed a particle known as axion. A particle that, at least mathematically, would resolve anything and would solve this CP problem once and for all. And for many years, a lot of scientists actually agreed with this proposition. Axions made a lot of sense, mathematically everything kind of added up, and what's even more interesting here is that at the same time these axions would once and for all solve the problem of dark matter, because if axions indeed existed, they would also be produced in such amounts that it would definitely explain the dark matter that we can't seem to find anywhere. And so naturally the scientists decided to try to discover this particle. A lot of experiments have been conducted since, I guess, 1977, since the original proposition. And a lot of them were trying to discover these mysterious axions that would actually solve two problems at once. The problem of not seeing dark matter and the problem of CP symmetry, also known as strong CP problem. The first and I guess the most famous such experiment is this one right here, the experiment known as ADMX. But even after a few decades, nothing so far has been found. And the question here is, how come? Why not? Where's this particle? And I guess some people and some scientists would instantly say, well, this is a waste of money, there's probably no such particle, and we're not really going to find anything here. But that's a very premature conclusion, simply because of what we know about other particles such as neutrinos. Neutrinos are these very strange particles that were initially proposed back in 1930s, and they're denoted as this letter right here. These particles have a very peculiar property in that they don't actually interact with a lot of matter. They only interact with things through the weak force, and also they exert a little bit of gravity, but at the same time they move really fast, close to the speed of light, and they seem to go through most of the matter. In this picture, they're created in the middle of the star and they easily go through the star, not interacting with any of the matter on the way. And because of this, it took a long while for the scientists to finally confirm the existence of neutrinos. As a matter of fact, it took almost 30 years. And their confirmation led to the Nobel Prize, because theoretical prediction here and the actual physical proof of the existence was a big deal. But just like with the neutrinos, the proposition for axions also suggests that they're extremely small, have very small mass, and they also don't interact with anything except for through the weak force once again. But in this case, the predictions suggest that their interactions are even less pronounced than the neutrinos, meaning that they're going to be even more difficult to discover and to confirm. And worst of all, their actual mass, or basically what we're going to be looking for, is currently unknown. Nobody actually knows what to look for and how to find them. But because of all of the previous experiments, we now are pretty sure what they're not. In other words, certain masses have already been eliminated because nothing was discovered. But unlike neutrinos, axions seem to have a very interesting property that can help us discover them. That property is connected to their interaction with the magnetic force. The theory here predicts that if you were to place an axion into a strong magnetic field, it will actually turn this axion into a relatively high frequency light, or basically high energy light, for example, X-rays. And so, for example, if we look at something that has a magnetic field, such as our sun, and if we start seeing X-rays or some other high energy light coming from these regions, it might indicate that what we're looking at is essentially the creation of these unusual axions and their interaction with the field itself. But using our sun for this is a little bit difficult because it produces so many different things, and this data can be interpreted in different ways. We have to find something that has a high magnetic field, but doesn't actually produce a lot of other energy, that doesn't really have a lot of exciting things going on. In other words, we need to find something boring, something not very active with a magnetic field. And it just so happens that there are 7 such objects. And here's a small image of one of them. These objects are known as the Magnificent Seven, sort of named after the old western from the 60s. And each of these boring objects is a neutron star. But it's not a pulsar, it's not a magnetar, it's just a neutron star completely by itself that doesn't seem to possess anything around it and doesn't seem to create a lot of exciting or powerful energy. And as of today, we found 7 such objects at a distance of about 400 to maybe 1500 light years away from planet Earth. All 7 of them are individual neutron stars that are slowly cooling down, doing nothing else in the process. They're all relatively young neutron stars, they're under 1 billion years old, because after this they're going to become pretty much invisible to us. But because we can still see them, and because we know neutron stars have very powerful magnetic field, studying these neutron stars is extremely important to study these various effects around strange objects with very powerful magnetic fields. Now we know that pretty much most neutron stars will have a very powerful magnetic field, with the strongest one being around a magnetar, but even a typical pulsar like Vela pulsar will have extremely strong magnetic interactions. We've seen this many times. And so because of this we kind of understand what should be happening around these stars. But because these 7 stars are so quiet and, well, technically kind of boring, discovering something unusual around them, that's when things become more interesting. And that's kind of what the scientists whose paper you can find in the description below discovered when they were trying to study these 7 neutron stars by using the XMM Newton observatory that essentially specializes in X-ray radiation. But quickly back to axions. We know that axions can be produced inside stars. We also know that there is a certain effect inside neutron stars that should be also producing a lot of axions as well, at least theoretically. And we also know that when an axion leaves the neutron star or anything that has a magnetic field, it should then interact with the magnetic field, creating relatively powerful radiation such as X-rays. And it just so happens that all 7 of these, the Magnificent 7 neutron stars, were producing extra X-rays, and these extra X-rays could easily be explained if this was actually axions producing them. Although the scientists in this paper do actually say that we need a lot more studies first, and this is not really conclusive yet. This is only a preliminary finding. And because these extra X-rays have no good explanation just yet, it kind of makes sense to investigate them in more detail. Now, of course, it's possible that something else is producing these extra X-rays. Maybe it's from some other objects we're not seeing in the system, but because all 7 seem to be producing them, that's kind of mysterious. That's very difficult to explain. At the same time, since we know that neutron stars cool down by emitting neutrinos, in other words, they have a lot of neutrinos coming from inside of them, it would sort of make sense that something else was happening inside and producing some sort of other particle that was then producing these extra X-rays. And so far, the theoretical proposition of Axions makes the most sense here. And if this is the observation of the mysterious Axions, it can actually solve a lot of mysteries at the same time. Dark matter obviously, CP symmetry, but also the mystery of FRBs or fast radio bursts. There are several propositions that suggest that Axions coming from within magnetars could definitely produce fast radio bursts, for pretty much the same reasons as the X-ray observations from the magnificent 7 neutron stars. Let's assume for a second that we wanted to calculate the total mass of matter in the universe. How would we do this? Hello wonderful person, this is Anton, and today we're going to be talking about the new study that seems to have calculated relatively accurately the total amount of mass of various types of particles and various types of things in the universe. So let's talk a little bit more about how they did this and what all of this means. First of all, as you can see from this simulation, there are a lot of galaxies in the universe. Every single spot here is a galaxy. Trying to calculate the total amount of mass in here would be a very difficult task. In order to calculate mass in the past, a lot of scientists used several different techniques. For example, by studying various gravitational effects and gravitational lensing effects from distant galaxies, distant stars, and distant galactic clusters, and then using statistical analysis to try to estimate the total mass of various types of matter in the universe that way. Other studies used what's known as baryon acoustic oscillations, sometimes also referred to as the acoustic waves of the universe, to try to estimate mass this way. This is a pretty complex technique, and we'll probably discuss this in some more detail later on. Other studies have used cosmic microwave background and looked at the tiny variations in the cosmic microwave background to try to estimate the total mass of the early universe and, of course, thus suggest the total mass of the current universe. And other studies have used type 1a supernova and their luminosity differences, many of which have been discovered in very distant galaxies, to thus try to estimate the total mass of the universe once again. But for the most part, when trying to analyze the universe mass and trying to understand how massive the universe is, we still have to try to use simulations. In other words, what the scientists usually do is create all sorts of numerical or even computer simulations, and then they try to compare the results from these simulations to the results from the experimental observation. And in this case, this is once again what the scientists did, but they used a completely different technique to try to estimate the total mass of matter in the universe. The technique that's somewhat similar to how we usually discover masses of planets and masses of stars as well. This technique relies on the orbital observations and various types of motions of different galaxies inside the galactic clusters. In other words, the scientists essentially calculated the speed of every galaxy in a specific galactic cluster to thus estimate the total mass of the cluster itself. And for this, the scientists behind the paper you can find in the description below used the data of approximately 1800 different galactic clusters, each of which contained up to 100 different galaxies in them, all taken from the very famous SDSS, or the Sloan Digital Sky Survey, which has been releasing data for many years now and has accumulated a tremendous amount of data from different galaxies out there. And on top of this, a new technique was developed that would allow us to study these galactic clusters in the future with even more detail, the tool that the scientists refer to as GalWeight, or I guess galactic weight. But I think it's also important to understand what all of these observations and analysis are based on in terms of theories. Today we believe that as the universe was expanding, as matter was propagating through the universe, at first most of it was not clumped and was distributed relatively equally across the universe, especially following the period that we refer to as the inflation period that most likely caused the universe to expand very suddenly and very quickly. And if we were to equally spread the mass of the entire universe over this volume, you would find something like 6 hydrogen atoms per cubic meter. But this is a very simplistic approach because here we're ignoring two things. One is that most of the matter seems to be not the visible type of matter, it seems to be the invisible, mysterious dark matter. And in the past few years, we've received even more evidence for this to be the case. On top of this, most of the mass didn't really distribute equally and was more or less clumped into these very long stretches of matter that we refer to as the cosmic strings, along which several different galactic clusters started to form, which then turn into galaxies. So instead of universe looking something like this, like equally distributed hydrogen atoms, today we know that it most likely resembles something like this if we were to somehow be able to see all of the matter, including dark matter, in more detail. But because of this matter collapse and because of the way that the matter spread across the universe, this makes it very difficult for us to try to calculate how much of it there is. But if we take a few of these clusters and measure their masses, we can then kind of try to imply the total mass of the entire universe by comparing all of this to the simulations like this one that we run on various supercomputers on the planet. This one specifically is from the supercomputer known as the Illustris project. A more simple way of seeing all of this is, well, okay, if we have a lot more matter, we expect this to result in a lot more galactic clusters across the universe. Whereas if there is less matter, we expect there to be less galactic clusters. And so by measuring the observed versus predicted number of clusters, we can thus imply the total mass of the universe once again. But since we can't really see dark matter very well except for gravitational lensing effects, in this case, dark matter can also be seen by measuring the total speed of galaxies orbiting around one another in a galactic cluster. The higher the total mass of the galactic cluster, the higher the velocity of orbiting galaxies. So this is one way we can calculate the total mass, including the dark matter, in a typical galactic cluster. And by using this technique, the scientists were able to create a relatively accurate estimate of total matter in the universe. It's now at 31%, with the 69% being the mysterious dark energy that for one reason or another seems to be pulling everything apart in the universe. Now obviously this doesn't provide the reasons, the answers to why, it only provides the observations, the what. And inside of this total matter that represents 31% of the entire universe, around 80% is the dark matter and only about 20% is the matter we see, the matter that we interact with, and the matter that's familiar to us. In this case, it's described as stars, galaxies, and dust and gas. And overall, this represents a very similar answer to some of the other techniques, with only a little bit of discrepancy, meaning that this Galway technique will possibly allow us to create even more accurate results in the future as we get more galactic clusters and as we get more observations from different telescopes. But at the same time, what all of this means is that of the entire universe, of everything in it, only 6% of stuff is visible to us, and we can only efficiently study those 6%. 94% of the universe is just unknown. It's really difficult for us to understand, it's very difficult for us to actually analyze, and it will definitely take decades to try to figure out why 94% of the universe is dark, unknown, not easily comprehensible to a human mind. And although some studies have suggested maybe we just need different types of physics for all of this, and maybe we haven't really understood gravity as we thought we did, other studies have suggested that there are just a lot of different subatomic particles that can exist out there and can produce these really extreme effects. Many of these particles have already been created in the famous CERN particle accelerator in Switzerland, and many of them have already explained certain things. But there are so many more particles technically possible, which really just means that there are currently too many explanations, and finding the specific one is currently very difficult. But the most important part of this study is that our observations using different techniques to measure the mass of the universe and the mass of stuff in it, for the most part seem to be agreeing with one another. The measurements from supernova, the measurements from gravitational lensing, and the measurements from the speeds of galaxies as they orbit inside of these galactic clusters. All of these measurements seem to have very similar results, suggesting that maybe what we're seeing is correct, but we just don't really have any answers to explain why we're seeing this right now. And why certain galaxies, like this one right here, Dragonfly 2, seem to possess so little dark matter in them in comparison to some of the other clusters that seem to possess a lot of dark matter. And that's once again only because we're unable to see so many different things. Currently we can only observe 6% of everything in the universe. Hello wonderful person! Today we're going to be talking about a study that suggests something unusual is hiding in the dark voids of the universe. something that could be responsible for the mysterious dark matter. But all of this is like super complicated, so let's dissect this a little bit in more detail, and welcome to What the Math. First of all, what exactly is dark matter? At the moment, nobody really knows, but the best mathematical explanation that we have is from the very famous Albert Einstein. It's something that's coming from his field equation, and he believed for the longest time, until about 1932, that this was a mistake. It's this value right here. But then, in 1932, when Edwin Hubble discovered that the universe was expanding, this value suddenly started to make sense. But scientists for decades believed that this value was actually zero. Oh, and yeah, one thing I forgot to mention is that this lambda represented the so-called repulsive force of the universe. Essentially, it's something to contradict the gravity, which would explain why the universe didn't just collapse after it was created. But in 1998, the scientists also discovered that it seems to be a value that's not a zero, it's actually positive, suggesting that the universe is not just expanding, it's also accelerating. And ever since then, this so-called dark energy, or the unknown energy, didn't really have a very good explanation. But this dark energy, along of course with the dark matter, are currently the best explanations we have for what's sort of happening with the universe and what we're observing around us. Now, the dark matter is obviously a completely different story, but it does have more explanations and also more potential particles that could be responsible for the effects we're observing. On the other hand, dark energy, which as you can see represents about 68% of the entire universe, is a lot more mysterious. And here, this is where scientists currently don't really know how to explain it. There's really no good one theory to try to identify what's happening. And so most of the time what you'll hear theoretical physicists say is that this is just like a fundamental thing. It just happens because, well, it's in a mathematical formula. But not everyone is happy with this explanation, and most importantly because nowadays we're also having trouble explaining this expansion, because this formula suggests that expansion is sort of uniform in every single direction. But the new observations from pretty much most of the modern studies suggest something completely different. The expansion is not uniform, it's accelerating but in different sort of speeds at different times, and there's something else going on here. Because of all of these unusual, unexplainable phenomena we're observing, a lot of scientists today, are trying to see if there's something else happening, specifically something that could maybe explain with some sort of a particle, some sort of an unusual object, or some other theory that existed for a very long time. And this is actually one such explanation. It's based on a theory from 1960s by the extremely brilliant Soviet theoretical physicist Erest Glynner, who essentially proposed this unusual object that was sort of like a black hole, but in some sense was actually almost the opposite of a black hole. It wasn't a white hole, it was something he referred to as geode, or generic object of dark energy. And these geodes from the outside would actually resemble black holes, but instead of having a tiny singularity that's essentially like a really massive object, these objects would be made out of dark energy, and here I'm going to take a little bit of artistic freedom and make them look like this. So these geodes, these unusual objects, would have very similar effects to black holes in some sense. They would still be able to absorb things, but they would also be repelling matter and would be creating these unusual effects that are literally dark energy. The mathematics of how these objects are created and maintained is actually very solid. There's nothing sort of unusual or extraordinary about them, but the extraordinary thing about these objects is how they affect the universe. So first of all, unlike black holes, which geodes would be mimicking in terms of physical appearance and also various other effects, they're still very sort of exotic and completely counterintuitive. One major difference here is that unlike black holes, these objects actually gain mass with time. And the way that they grow in mass and in size is through, well, kind of very similar to how the redshift works for example, light traveling across the universe. Today we know that with time and with space, light loses energy and becomes more redshifted. What most people don't realize is that something similar happens to mass. Objects actually lose mass with time and with distance, and this redshifting is apparent across the entire universe. But for massive objects, this effect is very minuscule. But for geodes, this is something that most likely increases their size and of course their effects on the universe as the time goes on. In other words, the scientists behind a lot of these different papers suggest that a typical geode that existed for billions of years would actually gain up to about 100 times more mass as compared to when it was much younger. And that's simply from existing, from traveling across time and space, not even from absorbing anything. Now, as I mentioned, it's sort of counterintuitive and doesn't make sense, but a lot of different papers that came out in the last few years suggested that not only can these objects exist, but they also explained how all of these exotic objects could easily form in the beginning of the universe in the first few millions of years, essentially from direct collapse from the primordial matter. So some objects would create stars, some objects would create black holes, but around 2% of these objects could technically create geodes. This is mathematically possible. And if these 2% create these geodes, it would completely explain all the dark energy effects we're observing today, and all of this technically, mathematically makes complete sense. But these geodes can also collide with one another, and their collisions would look very similar in terms of gravitational wave interaction to what we're observing from black hole collisions. One of the first papers that came out after the original unusual detection from a LIGO detector a few years ago was essentially about the possibility of one of these black holes, or possibly even both of them, being so-called geodes. The reason for that is that because they were just a little bit too massive, they didn't make sense. Most scientists never expected to find black holes of that mass. And the most recent detection of the unusually massive black holes even makes more sense for them to be geodes. Essentially, because the recently detected black holes were roughly around 5 billion years old, this would give them enough time to grow in mass if they were geodes. And this would explain what we're observing. At the same time, because of the unusual observation when the collision occurred, many of these things are a lot easier to explain if these objects are these exotic geodes and not black holes. But that's of course something we can't really prove right now. We know for a fact that black holes exist. I mean, we have an actual picture of one, but we don't know if geodes are real and if they're even possible. Only mathematically possible. So for now, we're just going to make an assumption that they do exist. So what does the new paper suggest? Well, the scientists crunched the numbers, they did a little bit of analysis and discovered that if you were to take all of these geodes and place them in the voids around the universe, which we found a lot of, including of course the nearby local void that's not marked here, and also if we were to assume that about 2% of all of the stars in the early universe created these geodes, it would totally explain the effects we're observing from the so-called dark energy. In other words, what these scientists are proposing is that inside of every one of these voids, there are just as many of these geodes as there are stars in the universe. And each of them is sort of responsible for, well, first of all, interacting with one another, but also pushing things apart in the universe itself. But since they do resemble black holes from the outside, it would be very challenging for us to prove their existence until we discover more about them and their exotic nature. But this recent study from University of Hawaii researchers also identified a few other very unusual features that could maybe help us identify these objects in the future. For example, certain ultramassive quasars or very powerful galactic objects really far away sometimes are way too massive. This mass cannot really be explained with modern physics. And in this case, maybe these are also very massive geodes producing some really strange and unusual effects that could be different from typical black hole effects. But unfortunately, because these objects are so far away, it's somewhat difficult to tell for sure. At the same time, mathematically, the scientists also realized that these objects would have a strange spinning layer above the surface. And this spinning layer, depending on the speed, affects the behavior of a geode. If this layer spins relatively slow, these geodes will most likely start colliding and combining into larger and larger objects. But as they're doing so, as they're growing larger and larger and as they're gaining momentum and start spinning faster and faster, at some point, as soon as they reach really high rotation velocities, they'll start repelling objects around them and essentially acquire these very powerful dark energy effects, while at the same time also affecting one another and repelling one another, creating these void bubbles that we're observing in the universe. In other words, if such a geode, for example, passed very close to a galaxy, it might disrupt a typical galaxy like the Milky Way and destroy it completely. But because all of these geodes are stuck inside of these voids that were most likely created because of these interactions, they for the most part only interact with one another and nearby matter that they repel, creating these very unusual empty bubbles. But naturally this would also explain why none of these geodes are destroying our galaxy, for example, why nothing around us seems to be repelled and destroyed by these objects. And so if these phenomena can be somehow confirmed, this would create a completely new class of, well, everything. This would most likely redefine our physics again and would allow us to slowly start understanding the universe a little bit better. But just like with the initial discovery of black holes, we kinda have to be careful here and take this step by step. A lot of new research and observations are needed, and the observational proof here is absolutely crucial before we can definitely tell if these objects exist or not. At the same time, different types of black hole collisions, for example, could one day help us identify if any of these objects are geodes after all, by looking at the actual ringing effect of the black hole collisions. Once we get better at identifying these effects, we'll probably have better answers. For now though, we can only assume that maybe this exists, but also maybe not. If however they do exist, it would suddenly provide a very good explanation to a lot of things we observe in the universe, including dark voids, including dark energy, and of course explain why the universe itself is expanding at different rates in different places. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries in regards to the mysterious dark matter, and more specifically a potentially really good explanation for why in the last few years the scientists have been finding certain galaxies that don't seem to have any dark matter, with the explanation providing evidence for how those galaxies are made. But in this case, we are obviously working off the assumption that dark matter itself, the phenomenon that we refer to as dark matter, seems to be some sort of a particle or some sort of actual matter, not a phenomenon caused in our misunderstanding of the gravity, or the phenomenon that can be explained by modifying certain formula, which is of course not something that has been proven yet. As a matter of fact, this is one of the biggest mysteries of the universe. The effects of dark matter are visible everywhere, even in certain really massive galactic clusters like the famous Coma cluster, but what causes it is not known. So anyway, in this case I wanted to actually start the story with the mystery itself, and this only started back in 2018. It started with this unusual galaxy that you can barely see in this image from NASA. It's known as NGC 1052 DF2, and we've discussed this galaxy many times before. But it also seems to have a relatively close neighbor that also seems to look very similar to the galaxy. That particular galaxy is known as DF4, and to everyone's surprise, when the scientists originally found these galaxies, unlike your typical diffuse galaxy or a typical dwarf galaxy, these two galaxies seem to possess practically no dark matter whatsoever. Now how do we know this? And that's actually important to understand. The way that the scientists study this today is by looking at the motion of various objects in a galaxy, something that's often referred to as the galactic rotation curves. Now, in a galaxy that possesses dark matter, we usually see something that you see on the right side. All of the stars here generally have the same velocity, even though logically you would expect the stars on the outskirts to move a little bit slower, just like planets do in our solar system. This doesn't happen. They move pretty fast. But with these two diffuse galaxies, when the scientists looked at them, they realized that the stars in those galaxies were doing something different. They were doing something that's similar to the left side, moving way slower than they should, suggesting that the total mass of the galaxy was extremely low, way lower than it should be if it does have any dark matter in it whatsoever. And by the way, here they're not actually measuring stars, they actually measure the velocity of so-called globular clusters. So basically objects like this that you see right here next to our own galaxy. And these are, because they're so bright, are extremely easily visible even from far away. And so several different explanations were given for this, and many explanations kind of at first made sense. But one of the more recent explanations involved the idea of nearby large galaxy known as NGS 1052, with the galaxy somehow responsible for the absence of dark matter inside these two. Then, just a few months ago, the scientists started to discover even more galaxies that don't seem to possess any dark matter. With the most recent discovery being the galaxy you see right here, known as AGC 114905. It doesn't actually look that green, this is just a representation of hydrogen gas in this galaxy, whereas the stars appear in blue, but once again, no dark matter present in this galaxy either, and there were actually 6 more galaxies discovered not so long ago. And so all of these galaxies together now sort of present a mystery. What exactly is happening here? Specifically because when it comes to these small diffuse galaxies, the original proposition has always been that they should be actually more enriched in dark matter. As a matter of fact, by mass, they should actually have way more dark matter than we see in these galaxies, which is normally the case with most diffuse and dwarf galaxies, just not these ones. And so some of the initial explanations were basically in regards to, okay, maybe we just miscalculated, maybe the distance here is wrong, maybe the actual velocity is wrong, or maybe the observations themselves are just wrong. And so many scientists try to confirm this, and every study so far has confirmed the original observations. These galaxies seem to be exactly where the original paper suggested they are, and everything seems to be as originally suggested. And this implied that maybe our understanding of how the universe itself works were just incorrect. Maybe dark matter is not exactly what we think, or maybe something here is just completely broken in terms of our physics. But obviously nobody wanted that explanation. And so some of the recent studies decided to obviously explore this more, but this time using computer simulations. In this case, simulating the evolution of a small piece of the universe that was approximately 60 million light years across, but focusing on approximately 13.8 billion years of evolution, basically from the beginning of the Big Bang until now. There are quite a lot of these simulations that you can actually find for free on the web already, with the famous one known as the Illustris project. But when they started this project, they didn't really expect a lot of galactic collisions and a lot of other things that they eventually observed. And having run the simulations, the scientists found 7 extremely intriguing galaxies that they gave relatively funky names. The names like Deer, Blue, Bird, Long Hair, and the ones you see in this image right here, with my favorite being the Wild Potato. And, to their surprise, all of these galaxies were devoid of dark matter, just like the ones that were discovered in the last few years. But where did it go? Their simulation revealed that it was actually due to the galactic collisions with nearby galaxies that were at least 1,000 times more massive, with the dark matter itself being stripped from those smaller galaxies through the interaction with these larger giants, which, by the way, was the conclusion with the missing dark matter in these 2 galaxies. Here, the nearby galaxy known as NGC 1052 and possibly its partner 1054 might have actually stripped these galaxies, with the dark matter disappearing somewhere in the middle. If you'd like to learn more, the video about this is somewhere right there or in the description below. And more interestingly, all of this only took a few passages close to a galaxy or a few near collisions. So basically all of this was extremely fast in terms of cosmological time. And it seems to be pretty common next to large galaxies, which also suggests that we should be finding more of these in the next few years. But more importantly, this does not require any modification to modern physics, to anything that we've seen so far, but also once again suggests that dark matter might actually be some sort of a particle after all. We just have no idea what kind of a particle and what to even look for. And that's essentially because the galaxies that were discovered in this study depended on the idea of dark matter in order to be created in the way that they were formed. With the next really important step being the idea of possibly finding a massive galaxy somewhere out there that's actually actively stripping dark matter away from a smaller partner. This would be a definitive proof of this particular proposition. And I guess the other proof here would be to see how many we can find in the next few years, to see if the simulation created the correct number of these galaxies compared to how many we believe exist out there. Although here it's also important to take a look at some other studies that have presented some other evidence about potential changes to dark matter over the years. Here once again we're talking about cosmological years. And here it relates to at least one study that tried to see how the galaxies and dark matter in those galaxies changed in the last few billions of years. In this particular case, the scientists in the study compared the mass distribution of galaxies really far away, approximately 7 billion years old, to some of the younger galaxies closer to us. In this case, taking a look at nearly 300 different galaxies out there. And by looking at approximately 300 different galaxies out there, they did discover a somewhat unusual pattern that's somewhat difficult to explain. It looks like in the beginning, so approximately 6.5 billion years ago, the so-called dark matter halo used to be much more concentrated closer to the center of the galaxy. And so even though today we believe it might look something like this, in the past it might have been much more concentrated and in effect much smaller as well. But it also had a relatively large region where the density was more or less the same. But second of all, created two different regions of density, with one being referred to as the core and one being the halo. And in this case, the scientists imply one thing. They imply that it cannot be explained if dark matter did not interact with other particles, which is basically the principles we believe today, where we think dark matter just doesn't interact with anything. In this case, the scientists imply that there has to have been some sort of an interaction with possibly protons, electrons, neutrons, to actually create what they're observing. Or at least there was in the past in order to create what we're seeing. And so here something might have changed over time and the dark matter might have evolved somehow. So basically yet another mystery to deal with for some of the future studies. And so here they believe that it's very likely that the dark matter was as we predicted in the beginning of the universe, but over time it started to interact with various particles and sort of spread across a larger area, forming the actual density we observe in the nearby galaxies. Once again suggesting that the distribution could be different depending on what part of the universe you're looking at. Or in other words, nobody knows. Hello wonderful person, this is Anton, and in this video we're going to be talking about a mystery coming from our own galaxy, related to some sort of an unusual energy emanating from a region where we didn't really expect to see anything. And it's also maybe something that will take us closer to answering once and for all what exactly is this mysterious dark matter. And to begin this, I wanted to show you a picture that was published by NASA, I think about 9 years ago, when we discovered this unusual formation around our galaxy. So if you were to look at our galaxy from this sort of side, or actually this is a much more appropriate orientation, you would see a very strange and very unusual formation right there. So these unusual bubble-like formations are today called Fermi bubbles. We've detected them pretty much completely by accident, but we've known about them for roughly around 9 years now, but we still don't really know what they are. NASA actually has tried to study them very thoroughly and discovered that there's a lot of radiation coming out of them, specifically things like X-rays and more recently gamma rays, and unfortunately there is no good explanation for neither how they were formed, what they are, what's in them, and what's causing this unusual radiation. We just know that they exist and that they are really large and that they're out there. And they're clearly connected to the center of our galaxy somehow, so maybe the supermassive black hole in the middle one day either absorbed some sort of a really massive star that emitted these unusual formations, or maybe the bubbles are somehow related to the astrophysical jets that you see here that were much larger before and then somehow dissipated the material in the formation that we see today. In other words, we don't really know. There's a lot of speculation, there's obviously a lot of attempts to explain these, but we just can't really explain what's happening. And one of the biggest mysteries in regards to these Fermi bubbles came from the ice cube neutrino detector that you see right here. This is in Antarctica. That's probably one of the most sophisticated detectors we've ever built. And it's this huge structure, as you can see, it's several kilometers long and is able to detect neutrinos coming from pretty much any direction striking our planet Earth. And very high energy neutrinos were detected coming from this region, which means that there is a lot of really high energy interaction with something. Now it could be some sort of really fast moving particles, but it also could be something more mysterious. Something we've been looking for quite a while now, the mysterious dark matter. But let's not rush into things and briefly talk about the actual scientific papers. So the first paper that was recently published, and you can see on the screen right here and find in the description below, literally talks about the detection of a lot of unexplainable gamma rays coming from the Fermi bubbles. So the energy that was created, but we just don't really know what made it. And it's been sort of like that for a long time now, and despite their best efforts to try to explain what's causing them, the scientists behind this paper have no good explanation. We just know that they're there, we just don't know what's causing them. And surprisingly, within a few weeks of that paper, someone else published this, where they actually do look at several unexplainable gamma rays and try to explain them as this mysterious dark matter. And this paper here doesn't actually even talk about the Fermi bubbles, it talks about other galaxies out there. Now, the reasoning behind this here is that in order for us to detect the dark matter, we obviously can't just look at the galaxy because there's a lot of interference here, a lot of other sources of various radiation, so we would have to look basically away from the galaxies in the so-called galactic halos, or possibly even just in the middle of dark space. And today most of the dark matter studies focus on three main ways of detecting it. Either by directly trying to create dark matter using the so-called colliders, basically these really large facilities that try to collide particles at really high velocities, or by looking at various effects that dark matter has on regular matter. But then there is a third way, and that's of course related to the particles that might be produced after the interaction with dark matter. In other words, these so-called secondary particles. A good example of a typical secondary particle is when, for example, the cosmic ray comes in from outer space, it starts striking the particles in the upper atmosphere, and the interaction starts producing this cascade of various secondary particles, including things like gamma rays that we can then detect back on Earth. In other words, the cosmic ray itself is sort of destroyed in the upper atmosphere, and it's the effects of cosmic rays that we feel down here and can even detect using things like Geiger counters. And so very similar secondary particles could actually be created by dark matter as well. And this is exactly what the scientists behind this paper did. They made an assumption that secondary gamma rays could be produced by dark matter, certain types of dark matter. And they started looking around the night skies, or actually no, they basically looked at all data of us looking at the night skies and identified several sources of gamma rays that were either in the middle of nowhere or could not possibly be explained. In other words, they looked at things like halos, galactic halos, or things like just middle of dark space somewhere out there, or regions very close to different dwarf galaxies that are known to have a lot of dark matter, and they tried to identify unexplainable gamma ray phenomena. And having identified pretty much almost 500 various unknown gamma ray phenomena, they then focused on 4 specific ones that they believed maybe were created by the mysterious dark matter. These 4 events were just the right type of energy, they also were in just the right position, and could be classified as the so-called light dark matter particle. In other words, they were able to show that certain types of gamma ray emissions could potentially be dark matter. And it just so happens that we have very unusual gamma ray emissions right here, and we can't seem to explain them. But don't get confused, this is not to say that this is definitely dark matter here and that this is what's causing these unusual gamma rays. We still need to investigate these gamma rays in a little bit more detail and compare them to the results from the other paper. But based on what these 2 papers have discovered and based on what we see right now, there is a slight chance that we might have finally discovered these signs of this mysterious dark matter that we just couldn't find before. In other words, it could have been always here, we were just not looking at the right thing. And what I really hope will happen in the next few months are a lot of follow-up papers that will hopefully explain the type of gamma rays we've detected coming from our own galaxy, and also maybe connect these gamma rays to the paper that describes them as potential dark matter discovery. In other words, we would really like to find out if this is what we're seeing. Are we actually seeing the dark matter interacting with matter and producing these gamma rays? And if so, great, we finally found it. If not, what's really causing these unusual formations and unusual gamma ray and X-ray emissions from these bubbles? I mean, something has got to be happening there, and we just need to find a way to explain what's going on. Otherwise, we're going to be stuck with even more mysteries to solve and even less theories to try to explain them. But that's of course the beauty of modern science, and also why there are so many scientific discoveries pretty much every single day. If you were to look at the amount of papers that come out in this particular field in astrophysics, it is just mind-blowing. And that really makes me hopeful that, well, first of all, gives me a lot to talk about on the channel, but also that we keep looking, we keep trying to find new things. And as a species, we're definitely really eager to discover new ideas and try to find new solutions to old problems. Hello wonderful person, this is Anton, and today we're going to be talking about yet another problem with the dark matter. The unusual ubiquitous, and omnipresent substance, thing, particle. We don't really know what it is, but it seems to be everywhere. But the new problem the scientists recently discovered seems to make it even more unexplainable than previously. So let's discuss this in a little bit more detail. But first of all, okay, well, a lot of people don't seem to believe dark matter exists or believe that something else can explain it in some way. And so naturally I wanted to start with a brief explanation why we kind of do believe that it's real and there is really very little reason to doubt it. First of all, the dark matter itself was essentially discovered when looking at the so-called galaxy curves or galaxy rotation curves as you see right here. If you look really closely, the galaxy on the left seems to have slightly slower spinning stars in it, whereas the galaxy on the right has stars moving a little bit faster. As a matter of fact, the motion of stars in a galaxy on the left is explained with the regular Newtonian physics. In other words, it's using exactly the same physics as what we use in the solar system to explain the motions of planets around a star. But the galaxy on the right has stars moving in a very different fashion, with the actual motion being somewhat similar to what you would expect from, for example, some sort of a spinning disk like the one you see here, where all of the points do move with a relatively similar velocity. Now naturally, we wouldn't really expect matter to move in such a way in the universe, but turns out that it does, and turns out that pretty much every galaxy we've seen so far is closer to what you see on the right, not to what you see on the left. This was a huge surprise when it was discovered by the brilliant Vera Rubin, who you see on the left, with the famous astronaut John Glenn on the right, although honestly they could have probably taken a better picture of them, unless she actually fell asleep during their conversation. Now unfortunately she passed away in 2016, which is ironically is the same year that John Glenn passed away, but nevertheless her legacy and her discovery of dark matter live on, and she has a new telescope named after her because of all of the original discoveries she made, and also because she never really managed to win a Nobel Prize, even though many people wanted her to be nominated for it for many decades. But the thing is, there are other ways for us to explain the galactic curves or the galactic velocity curves, and there have been many attempts, including the most famous attempt using MOND or modified Newtonian dynamics that tries to recalculate and redefine how we calculate the idea of gravity. Essentially, it modifies gravity itself. But there are obviously other ways for us to see dark matter, and one of these ways is the very typical Einsteinian effect known as gravitational lensing. And in this case, it's not the gravitational lensing you see here from a black hole, it's the one from galaxies themselves. Specifically, the effects usually created by tremendously large galactic clusters that possess tremendous amounts of the invisible, mysterious dark matter inside of them. And unfortunately, there is no other theory, including of course MOND that I just mentioned, that can explain any of this. The only explanation is that something invisible seems to exist inside of these galaxies and is causing these tremendously powerful gravitational effects. And so the assumption that dark matter is there and that it's causing these effects has always been there. And because we sort of have a general idea of what it should be doing to matter around us, various computer simulations have been made over the past years, including this right here that you see. This is known as Illustris project, that try to recreate the modern universe using these simulations and using the math and physics that we understand from dark matter. Now, all of these simulations seem to do a relatively good job at creating the universe we see, which by the way you can also explore yourself by using the Illustris project Explorer page and by essentially looking at the dark matter generation and the creation of various stars and galaxies as imagined by the supercomputer. And well, in a nutshell, they do produce a relatively accurate picture of the universe, including the mysterious cosmic web that seems to connect everything in the universe and seems to possess a lot of the dark matter particles on the inside. However, this is where we get to the new study, and actually several new studies that seem to discover something that doesn't really make sense. For example, the most recent release of the KIDS survey or Kilodegree survey that essentially analyzed the universe around us discovered that certain parts of the universe and certain clumps in those parts seem to be about 10% thinner in terms of the amount of dark matter in them than it should be. In other words, it was more homogeneous and didn't possess the exactly same amount of density as what we usually create in these super simulations in Illustris or other projects. Now, this is not really a big difference just yet. However, there were other studies, specifically most recent studies by using Hubble telescope, that focused on studying specific clusters of galaxies, very massive clusters that possess a tremendous amount of mass in general. And the paper that, as always, you can find in the description below, pretty much discovered almost the opposite of what was discovered by the previous surveys. And although it doesn't actually contradict the findings of the universe being a little bit thinner, it does contradict those findings when it comes to very specific clusters. They seem to have discovered at least 3 galactic clusters that seem to be much thicker in dark matter than they should be, about 10 times thicker. In other words, the gravitational lenses produced by these 3 specific clusters were like 10 times more powerful than they should be. And that of course only means that there is a lot more dark matter present in them and a lot more overall mass. Because we cannot see this mass, it can only be dark matter. At least that's the current assumption. The scientists behind this paper actually warned that, well, we hope that this is not some kind of a new mystery, some kind of a new dark something that we're actually discovering here, because hopefully this can be explained with current theories of physics. The last thing we need right now is another mysterious dark blank, dark something. And actually, as you can imagine, these ideas already exist out there. They're not really theories yet, but there have been propositions suggesting that there might be another some sort of a particle or energy that causes the universe to act slightly different from what we imagined. But I guess the question here is, how do we know that this is dark matter after all? Well, it's all really based on our understandings of how gravitational lensing works. Today we're pretty certain we know how to figure out how much mass there is between a bright object and some sort of a mass in front of it. In this case, the gravitational lensing techniques have improved so much that we can usually recreate an object that's even causing these effects or that's behind the gravitational lens. And at this point, we can normally calculate the mass of this object that's causing the lens to an extremely accurate amount. And so when looking at these gravitational lensing clusters and when trying to combine the total mass of the cluster, the scientists did discover that there was about 10 times more of mass than there should be, at least based on the observations of the visible matter in this cluster. And here's what this looks like with the visual light and the dark matter in blue that's being slowly introduced into this picture. This is essentially one of these clusters. This one is known as MAX J1206, and it's recently been kind of trending in the astrophysical community simply because of these discoveries. But here's essentially the composite image of all of these 3 major clusters, each of them possessing way more dark matter than we anticipated or believed was possible. And the most interesting part is actually shown right here. This is what's known as the nested lenses and are produced by the immensely dense concentration of dark matter present in each of these individual galaxies that sort of act like a typical collection of lenses, although in this case they're arranged in very different ways, and so the actual lensing effect, despite being very powerful, is not particularly useful at looking at objects behind them. And because today we can usually estimate the amount of mass and dark matter present in a galaxy by essentially looking at the total amount of light in it, the scientists were then able to calculate the mass of visible matter and compare it to the actual lens itself. And it turns out that it just doesn't add up. There's a huge amount of dark matter that's distributed here invisibly and across a much larger area, which is essentially what you're looking at here in this other image. And although to some extent, of course, this all makes sense because a more sort of dense and a more massive cluster is going to attract even more dark matter in it, and objects like, for example, galactic voids where there's nothing are going to have almost nothing in them, it still doesn't really explain to us why is it that these specific clusters are so much more dense, and why is it that the majority of the universe seems to be much thinner in the amount of mass and amount of dark matter present in the cosmic web. Now, one possible solution that could be solved by, I guess, Mond or similar theories is that maybe the gravitational influence is actually a little bit weaker than we thought, and so it doesn't really make the universe clump as much. Now, this obviously means that a few formulas have to be reworked once again, and this will obviously upset a lot of physicists, but at this point we actually have no good answer for what's happening and why this is so. Other explanations involve an introduction of a completely different concept known as dark radiation, so once again, dark something that we know nothing about. But in this case, this dark radiation doesn't explain everything, so another particle needs to be added into the equation. So yeah, we're basically kind of back to having more mysteries and more unusual effects and more unexplained phenomena. which actually means that there are still so many more mysteries to solve and so much more to discover. And this is of course the good thing. This means that I have so many more videos to make for you. Hello wonderful person, this is Anton, and today we're going to be talking about that other mystery of the universe, the mystery about which we know even less than any other mystery. We're going to be talking about dark energy. And specifically, we're actually going to talk about this new research that might provide at least one solution to one of the biggest problems we have, known as the Hubble tension. But to start, what is this dark energy and why do we even need this? Well, first of all, I guess it's sort of important to understand that dark energy was actually only discovered about 23 years ago, back in 1998. This was a huge and actually groundbreaking discovery based on the observations of various supernovae around the universe. And one of the reasons why it was discovered in 98 and not before that is actually because we lacked the technology and the telescopes to observe all of this. And so during that decade, as the scientists started to look around the universe and notice different type 1 supernova happening really far away from our galaxy, and here we're talking about hundreds of millions of years away, they actually realized that the universe wasn't just expanding as we previously predicted, it was also accelerating its expansion. In other words, the expansion of the universe was going faster and faster and faster the farther back in time you look. And to try to explain this acceleration, the scientists had to come up with a new term. In this case, the term was dark energy. It was this energy of repulsion of everything across the universe. But because of the total volume of the universe, even though the total amount of this energy represents about 70% of everything in the universe, its total density is actually extremely low. For example, if we were to take a random volume somewhere in the universe, you would actually find a lot of different particles there. You would also find some dark matter, but you would find extremely low amounts of this dark energy. But because the universe is so large and because there's basically a lot of volume to go through, overall this energy ends up to being about 70% of everything, with some of the estimates varying a little bit. So here about 27% is dark matter, about 5% is regular matter, so basically stuff we're made out of, and about 70% is dark energy. These numbers do vary a little bit from study to study, but overall they are usually about the same. And in case you were curious, about 12% of regular matter are atoms, 15% are photons, and about 10% are neutrinos. At least that's what it used to be like when the universe just started. At the same time, the discovery of dark energy also allowed the scientists to finally reconcile the problem with the early Einstein formula, which essentially had this term in it that Einstein threw away initially, but that actually explained the acceleration of the universe and essentially represented a kind of a constant in the universe. The universe was supposed to accelerate. And in terms of explaining this, it actually makes a lot of sense, especially because it sort of connects the idea of the universe with the ideas from the quantum mechanics, for example. But let me try to explain this so it actually makes sense. So, for example, if we were to take a balloon filled with air, as the balloon expands, the air inside the balloon will start decreasing in temperature because the balloon is using the energy inside to basically increase its volume. Usually physicists refer to this as doing work, so the stuff inside the balloon is doing work and expanding its energy. But now let's take the same balloon, but this time hypothetically fill it with nothing. It's going to be a vacuum balloon. And we're once again imagining a balloon that's going to be expanding for one reason or another. Now it doesn't have air this time, it's vacuum, but its total volume is going to increase in time. And this is something that's related to this formula from thermodynamics that essentially tells us that the change in pressure and the change in volume will always depend on the total amount of work that transfers the energy to the surroundings. But the thing about that vacuum balloon is that even though its volume is increasing, the energy inside is not decreasing. It actually is also increasing because of one concept from quantum physics. The concept that's visualized right here, the concept of zero-point energy. This refers to the idea in quantum mechanics that has been proven many times that in complete vacuum, there's still going to be the minimal energy everywhere. Every single point in that vacuum is going to have slight fluctuations which will actually produce all sorts of virtual particles. Or in other words, no matter how little energy there is somewhere, there's always going to be absolute minimum. So nothing in the universe can be completely energy free. It's always going to have this absolute minimum required by the quantum physics. And although it might sound counterintuitive, this has actually been proven by this experiment right here and several other experiments, and this was like decades and decades ago, where, for example, if you were to take two different plates and place them in a vacuum, the space between these two plates is not actually going to produce as much of this zero-point energy, whereas the vacuum on the outside is going to produce more. And because of this, there's going to be this pressure from both sides. In other words, even though these two plates are in complete vacuum and there should be absolutely no pressure produced whatsoever because there's no air, they're still going to be receiving pressure from these virtual particles and from this zero-point energy that exists even in vacuum. This is actually known as the Casimir effect and has been proven many times. And so since we know that vacuum itself will always have this absolute minimum energy in it, as you increase the size of that balloon that we talked about before, it means that as the volume increases, so does the total energy in the balloon. But in order not to contradict that formula I showed you before from thermodynamics, this means that one of the terms has to change, and in this case it's going to be pressure. So the pressure here becomes negative. And that negative pressure is the reason why the balloon starts expanding even more and accelerating even more. In other words, the combination of thermodynamics, the quantum mechanics, and some of the Einstein's theories explain the idea of dark energy really well. Although unfortunately they do not predict the numerical value very well. As a matter of fact, the predicted value versus observed value is extremely different, and that's one of the problems that we're not going to discuss in this video, but it's a problem that nobody has a solution to just yet. But the quantum mechanics and the zero-point energy still kind of provides the best explanation to why the universe is expanding. What it doesn't actually explain though is why is it that we now have new problems, specifically what's known as the Hubble tension. And though it sounds kind of complicated, it really isn't. It's super easy to understand. If we were to take this right here, which is the cosmic microwave background, and try to measure what's known as the Hubble constant, which is the acceleration of the universe, we get a value that's about 67 kilometers per second per megaparsec. In other words, for every 1 million parsec, the acceleration of the universe increases by 67 kilometers per second. But here's the thing though, as the scientists started to look around and, for example, use different stars, like this recent example with this paper right here, used a completely new technique using very specific types of giant stars that have very specific emissions that allow us to establish distances in the universe. And by using these stars, we can technically try to calculate the expansion of the universe again. Or we can also use certain types of supernova, which have been used in the past as well. But the thing is, once we start doing this and once we start looking at the expansion of the universe by using different stars and by using different supernova, the values start to kind of not add up anymore. Here's an image from NASA that was released a couple of years ago that shows you how different projects seem to calculate very different values for this Hubble constant. And although some of them do have a lot of error margin, some of them are extremely precise, but as you can see, they're actually very different from one another, with the average difference being about 5% or so. And that's a huge problem, and that is what we call Hubble tension. The values for this expansion of the universe don't seem to add up depending on the measurement. But there is actually something interesting about these values. It seems that the values from the early universe were actually a little bit lower than they are from some of the locations in the modern universe. And so when looking at stars and supernova closer to us, the value is about 71 kilometers per second per megaparsec, which sort of implies that the acceleration of the universe also increased with time. And that's not something that's easy to explain right now. But that's exactly what the scientists behind this paper that you can find in the description decided to do. They approached this mysterious dark energy as basically a kind of a substance that sort of changes its property in a similar manner that, well, I guess water changes its properties depending on the temperature. For example, if you were to look at water, when water freezes, it actually expands, and that's why ice floats on the water. Its density becomes slightly less than the density of liquid water because the ice crystals on the inside form in such a way that it basically lowers the total density. Now, the scientists in this paper kind of make a similar approach, except that it's way more complex, and make a somewhat similar assumption about this dark energy. They suggest, or they imply from their study, that the dark energy is also undergoing a kind of a phase transition. If in the early universe the dark energy existed in a slightly different phase, and as universe expanded and changed and cooled down, the dark energy transitioned into another phase, This would mathematically explain what we're seeing and basically would resolve this so-called Hubble tension. And so in this case, the dark energy in their model has gone through a transition of phase and lowered the total energy density. And by lowering the energy density, it thus changed the expansion of the universe. Or in some way, you can also see this as these tiny bubbles of dark energy being produced in the universe as essentially it changes its transition. Now the thing is, when they did the calculations, using the values and using the observations from cosmic microwave background, assuming that there was some sort of a transitional stage, the value that they got at the end was very similar to the value we get from other studies. And so their model actually did at the end get the value of about 71 kilometers per second per megaparsec, suggesting that maybe they are actually onto something here. Maybe this is indeed how we can resolve this problem of dark energy and the so-called Hubble tension. But because this is just one of many studies and one of many explanations, we definitely need a lot of follow-ups and a lot of analysis from other scientists as well before we can definitively say what exactly is happening with the universe, and more importantly, where exactly is it headed? What's the future of the universe? Is it going to continuously expand and accelerate and eventually reach the point known as the Big Rip, where everything sort of stretches to the point where everything becomes torn apart? Or is it going to be something entirely different? Is the dark energy going to transition again and change again to the point where things will maybe reverse? So that's something that's kind of curious for us to find out, but in some sense it's actually not something that's going to affect us anytime soon, simply because here we're talking about billions and billions and maybe even trillions of years. Okay, so let's see what the media is talking about today. A map reveals a cosmic void where laws of physics seem not to apply. Dark matter findings suggest Einstein may be wrong. It's gonna be one of those days again. Anyway, hello wonderful person. Just like every science communicator, at some point in life I learned that as soon as you mention Einstein was wrong, or talk about how laws of physics might be broken somewhere, it definitely captures everyone's attention. But I guess at some point you also start feeling really guilty about those headlines, and so I'm gonna try to avoid doing that in this video. But we are actually going to be discussing these particular findings because they are absolutely fascinating and, well, unfortunately do not actually prove Einstein wrong. As a matter of fact, quite the opposite, they prove him extremely correct, and they also show us that we sort of understand the universe extremely well. However, in this particular finding, there is one unusual discovery. I'll mention this near the end of the video. So what exactly are we talking about? We're talking about the Dark Energy Survey, also known as DES for short, and this is probably one of the biggest collaborations on the planet, except for maybe some of the other ones like the Event Horizon Telescope, that involved 7 different countries, 25 different institutions, and over 400 different scientists, some of whom you see right here in this picture. And the purpose of this survey, along with the actual studies behind it, is to kind of establish if we understand the universe, and if we understand what's happening in the universe, by trying to compare the theories of the universe, and specifically the theory we usually refer to as the Lambda CDM model of cosmology, and compare and contrast this model to the actual observations from different telescopes. Now in this particular case though, they only used one major telescope located in Chile, this one right here, and the telescope here is really famous because it also has this extremely powerful digital camera attached to it. A camera that they refer to as dark energy camera. And the purpose of the camera, as the name suggests, is to study the dark energy, the mysterious, I guess, substance or something that seems to cause the universe to expand faster. And because this camera has something like 570 megapixels in it, which is I think about 50 times more than the camera in my smartphone, and also because over the course of 6 years, from 2013 to 2019, the scientists also have been able to use this for over 750 nights in total, they were able to discover quite a lot already. Now, first of all, this is the 3rd year, the so-called year 3 of Dark Energy Survey, and here after 345 nights of observations, with about 1/8 of the night skies observed, they were able to uncover close to about 230 million different galaxies, and a lot of really interesting features in between those galaxies, including things like cosmic voids, with one visible in this particular image, and with a total number of these found standing at 3,222, while also confirming the idea behind the clumpiness of the universe, meaning that the galaxies are not just sort of evenly spread out, they are more or less clumped, forming what you see right here. This is what we refer to as the cosmic web. while at the same time also identifying several major gravitational lensing effects, all of which was exactly what they expected to find, and all of which was also required for them to confirm Einstein's theories, confirm our cosmological models, but most importantly, prove several major things. First of all, that dark matter seems to be real. As a matter of fact, this is probably the biggest proof we have right now that dark matter seems to be, well, everywhere, at least in those regions where they looked at. Or in other words, just as predicted in the lambda CDM models, at least 25% of everything in the universe seems to be the mysterious dark matter. And the way that they were able to see this is by looking at those various galaxies everywhere, and we're talking about close to about 230 million galaxies, using the redshift of these galaxies to establish the more or less precise distance to them, and then establishing the overall mass present in those regions by observing the weak lensing effect that you see right here, for example. This is one of many galactic clusters that have previously been discovered to have a lot of dark matter in them. And so in this image from Hubble, you can kind of see the lensing effect by something invisible but something really massive in this region right here. And so by using the combination of the gravitational lensing effects, which allowed them to more or less establish the total mass of dark matter present there, and by combining this with the observations of galactic clustering or galactic clumping, and looking back on this region right here that roughly represented the universe from today up to about 7 billion years ago, while also combining this with some really rigorous statistical analysis, which involved a lot of sort of blind analysis where you don't actually know what you're going to find, they were able to confirm some really major assumptions we had about the universe. First of all, we have to compare this to one of the previous major releases known as the Planck collaboration. This one was using the Planck telescope to literally try to study the universe by looking at this, the cosmological microwave background, or the so-called oldest light in a universe. Now, this was a very important discovery a few years ago, and there was a very important confirmation of our theories, but this only represented a snapshot of the universe approximately 13.8 billion years ago. It was really important for the scientists to see if the original predictions from these Planck observations would actually be confirmed by observations from some of the later universe, the universe today, for example. So would something similar be visible if we look at the universe 7 billion years ago, 6 billion years ago, or even closer to today, I guess? And so for this reason, a lot of unbiased, blind statistical analysis was used to try to establish some of these parameters, including, of course, the Hubble constant that we often talk about. And well, in a nutshell, 26 out of 30 papers released so far essentially suggest that pretty much everything we believed about the universe seems to be more or less correct. So for example, if we look at the Hubble constant or the expansion of the universe, the original value from the Planck collaboration was about 67 kilometers per second per megaparsec. In other words, for every 1 million parsec of distance, the universe expands by about 67 kilometers per second faster. In this collaboration, the value was a little bit higher, it was about 68.1, but still within the boundaries what the scientists expected it to be. Although do check out one of the previous videos where I actually go into some other studies that do talk about this mystery in a little bit more detail. But pretty much everything else in these studies suggests that our understanding of the universe from the previously mentioned lambda CDM model seem to be more or less correct. The observations in this case do indeed meet the expectations from the theories. Now obviously not everything, but for the most part they are more or less correct. There is, however, one thing that they were kind of surprised about, and this is why the publications you might have seen online mentioned Einstein being wrong and so on. The only tiny difference between the observations of Planck telescope and the more recent observations from the Dark Energy Survey seem to point at the very unusual fact that the universe seems to be a few % less clumpy than predicted. Or if we were to look at this more practically, the original models of the formation of matter in the universe and the formation of galaxies and so on does imply that everything should be a little bit more clumpy. Galaxies should be a little bit closer to one another, the cosmic web should be a little bit thinner and so on, and everything is expected to look in a certain way. But by using the observations from the last 7 billion years, the scientists discovered that the galaxy clustering was not as dramatic as they expected. Now here we're talking about just a small percentage difference, but it is significant enough to possibly create a new mystery. Something in the universe is causing the galaxies to not be as clumpy as predicted. Now obviously it does not mean that he was wrong and nothing is really wrong with the universe. It only implies that something out there is still mysterious and is not really easy to explain with just our current understanding of the cosmological theories. Something has to be modified, we're just not entirely sure what yet. No one is sure, and so it's a mystery, and naturally nobody is really wrong yet. And considering the fact that everything else in these papers seem to actually prove our ideas and our understanding of the universe, including proving the overall density of the universe, supporting the dark energy, supporting the cosmological constant, and of course predicting the relatively similar expansion of the universe as well, with just that cluster in amplitude being a little bit different from what was originally predicted, overall it presents an extremely important discovery that we sort of, as humans, tend to understand the universe really well, which is really surprising. I think a lot of scientists behind these papers were probably just as surprised that our original cosmological theories from a few decades ago seem to actually predict pretty much everything, almost perfectly. And once again, these papers prove that the dark matter seems to exist, the universe or the galaxies in the universe form the beautiful cosmic web you see right here, simulated in the Illustris project, and the galaxies tend to kind of come closer together, forming large clusters that we see everywhere, with a bunch of different cosmic voids in between them, and in this case it was 3,222 cosmic voids discovered. But I guess it's also important to remember that this is just the beginning. Remember, they only covered 1/8 of the night sky, and they also started this back in 2013. After a couple of decades of doing this, we're going to have a lot of really interesting data. Possibly a lot of confirmations of theories that exist today, but possibly a lot of new mysteries that we can't even imagine yet. More importantly though, the whole purpose of this is to try to discover what's happening with this whole expansion of the universe. It's still a huge mystery, nobody really understands exactly what's happening, and there are a lot of unusual observations coming from different studies. But one of the more important confirmations coming out of this is that dark matter seems to be real after all. It seems to be everywhere. We just don't really know what it is, or what it's made out of, or how to find it. We just seem to see the effects of it. Unless, of course, this has some other explanation. Right now, there is no better explanation. Hello wonderful person, this is Anton, and in this video we're going to be talking about the mysterious dark matter once again. Although, actually not the dark matter, but the opposite of that. One of the theories that tries to remove dark matter from existence completely and instead focus on trying to understand the universe without needing any dark matter in it whatsoever. So first of all, this is the paper. You can find this in the description below, and the main idea in this paper is that for the first time ever, the scientists studying so-called MOND, or the modified Newtonian dynamics, have been able to partially recreate part of the universe using the parameters from the MOND theory, and it surprisingly looked somewhat similar to what we really have in what we see in our universe. Now let me explain this in a little bit more detail, but before I explain this to you, I wanted to focus on why we still believe dark matter might exist. So originally, some of the first scientific papers about dark matter were actually made by this wonderful lady, this is Vera Rubin, who was the first to notice something unusual about the so-called galactic curves. In other words, she noticed that when we look at different galaxies, even though technically if we use Newtonian physics, we expect some of the farther stars here to move slower. Basically, the farther away they are from the center, the slower they should move, just like planets. In reality, we saw something like this. The velocity was much higher than we expected. 10 times higher as a matter of fact. And this was the first official confirmation of the possible existence of this so-called dark matter. But over a few decades now, we've collected a lot of other evidence as well. Like for example, there are these unusual gravitational lensing effects coming from what seems to be empty space. And some of these gravitational lenses are extremely powerful, and this would be very difficult to explain with just the visible matter. We've also noticed that there are quite a lot of these so-called dark matter galaxies, or essentially galaxies that have some stars, a few visible stars, but for the most part they actually behave like a typical galaxy. The stars here move pretty fast, suggesting that something is holding them together. We've also seen various interactions in galactic clusters, and I think the most famous one, and the one that's usually used to prove dark matter, is the so-called bullet cluster, where several galaxies collided, and we've observed the interaction between regular matter and what appears to be this unusual invisible matter as well. And all of these effects to us, to modern scientists, suggest that dark matter might be a real thing. There are actually a few more examples as well. I'm not going to mention all of them in this video, and I've also mentioned some of them in previous videos, but the idea is there. But the problem is, for the past, I guess a few decades now, all of our attempts of finding dark matter using relatively expensive experiments have not really been successful. There were some partial successes, but nothing where you can totally say that we've just discovered it. Which is why many alternative theories have been proposed over the years, and the one that's probably most accepted today, the one that's sort of alternative and not too crazy, is what's known as MOND. Modified Newtonian dynamics, originally proposed by this person right here, Mordechai Milgram, who essentially suggested that we could actually explain these observations if we redefine the way gravity works at faraway distances. In other words, he suggested that even though for a typical galaxy close to the center, you'll still observe Newtonian effects, as you move away from the center, the farther away you get, the more unusual the effects get. And the way that this theory works in a nutshell is, well, it explains the Newtonian physics or Newtonian attraction between two bodies by involving distance as well, but in a very different way. In other words, up to a certain distance, the attraction between various bodies is relatively similar, but as you move away from the center of the galaxy and the acceleration becomes lower, such as here in the outskirts of a typical galaxy, the attraction between bodies becomes considerably stronger, explaining why galaxies don't fall apart even when stars move this fast. In other words, it reinterprets the gravitation formula for faraway distances. And this is something that does explain a lot of things in the universe, including, of course, the previously mentioned galactic curves. But the biggest thing that it could not explain is the creation of the universe itself before. Basically, all of our modern computer simulations using supercomputers are always able to simulate relatively accurate galactic representations. This is basically what's known as universe in a box, using the theory that accepts dark matter, also known as lambda CDM model. This is the model where we think dark matter exists. And basically this is the most accepted theory right now. So for example, in this project here, this is known as the Illustris project, the actual galaxies generated are extremely accurate, but this does use dark matter. We've never before been able to do this with other theories. But this paper, for the first time ever, was able to generate this universe in a box, but using no dark matter. And according to the scientists, it's more or less correct. It's more or less something that we can compare to the real thing. Which is great news for the scientists that don't believe in dark matter and think that the MOND model explains it a lot better. Now, it obviously still doesn't explain some of the other things we're seeing, like for example, the previously mentioned bullet cluster that you see here is still kind of difficult to explain, or actually impossible to explain using the MOND model. And also some of the other effects, like the gravitational lensing effects, are also not particularly MOND friendly, but nevertheless, this new simulation definitely is a great step for possibly explaining the universe without the need for dark matter. Now, the takeaway message here is not that dark matter does not exist. It's just sort of a new explanation to how we can see the universe differently. And despite the success of this new simulation, we still need to work out a lot of other problems that the model has. But according to the scientists behind this paper, some of the things simulated in their model was even better than in the traditional dark matter model. Like for example, they were able to generate clusters that were a little bit more realistic, while at the same time their model was also able to generate quite a lot of various galactic disks, like the one you see here, and the one that's very similar to the Milky Way in a sense. And this is something that's not usually that easy for other models. While at the same time, the scientists also mentioned that for the most part, when the simulations use dark matter in them, these results are normally very sensitive to the location and the number of different supernovae. So in some situations, not a very realistic galaxy is created if the supernova numbers are incorrect. And in the MOND model, it didn't really matter as much. But nevertheless, there are still some major problems with this as well. One of the biggest problems here is that according to the MOND model, the speed of light and the speed of gravity is not exactly the same. But since 2017, when we started measuring gravitational waves, we discovered that both speed of light and speed of gravity are actually the same. So in that sense, MOND model is not really correct. At the same time, certain motions of globular clusters are not easily explained by Mond model either. As a matter of fact, they're usually predicted incorrectly, whereas globular clusters we see in reality do seem to follow a more lambda CDM-like motion. In other words, the dark matter motion. So in that sense, there are still a lot of questions to be answered for both of the theories. Or technically, it's not even a theory yet, it's just a hypothesis. And neither of these theories can be disregarded or disproved very easily. They both have quite a lot of interesting ideas that are quite supported by various scientists. As a matter of fact, Vera Rubin herself, who passed away only a few years ago, started speculating near the end of her life that maybe we need to redefine how we see Newtonian gravity. So in a sense, she believed in a kind of a Mond-like model and slowly moved away from believing in dark matter as an actual particle. Most of this came from the fact that over the decades, they kept predicting that we're going to find dark matter at some point, but nothing was coming out of it. So something else was happening with the universe that we just didn't understand just yet. But in all honesty, what I personally think is that neither one of these models is perfect just yet, and neither one of these explains things the way they really are. There's probably something else happening here, we're still not really sure what, but discovering these things is going to be one of the biggest groundbreaking discoveries of the 21st century, hopefully. I mean, hopefully we discover what's happening here, because, I mean, it's been driving a lot of scientists pretty crazy. And because even today we have so many experiments already running and so many more that are planned for the future, I'm sure in the next 30 to 40 years we'll finally be able to solve this mystery. At this moment, I'm personally not even sure what it is anymore, but because none of the theories provides an absolutely perfect answer, this is why it's a little bit difficult to say with certainty. Which is of course where we go back to the original idea of scientific process. We have to get enough evidence to support our idea before it becomes a fact. Right now, none of this is factual. But hopefully in our lifetime we'll be able to explain what's going on. Otherwise, a lot of people are just going to be very dissatisfied. Anyway, on that note, once we discover more, I'll make sure to follow this up with another video, but for now you can check out the paper that I mentioned in the description below, and some of the pictures from the simulation are available in it as well. And before we finish, well, it's very unfortunate that Vera Rubin passed away without ever winning a Nobel Prize, and many people believe that she definitely deserved it, but a few months ago, to commemorate her name, this beautiful observatory was renamed into Vera C. Rubin Observatory. This is actually an amazing device that's going to help us understand the universe in a lot more detail. And in the next few years, we'll be hearing a lot more about this particular observatory because it's going to be making a lot of new discoveries. Hello wonderful person, this is Anton, and today we're going to be talking about a new announcement coming from a very interesting experiment that suggests something unusual may have been detected, and that something may have also been the mysterious dark matter. So over the last few weeks there were quite a lot of different news coming about this experiment, but most of the headlines were basically suggesting that we did discover dark matter after all. And more specifically, the claim was that the scientists were able to see the mysterious Axions, the mysterious particle that's supposed to explain the existence of dark matter and also solve a very unusual phenomenon in physics that still hasn't really been explained. But all of these topics are actually really complex, like super complex, so it took me a while to try to figure out the best way to explain all of this. And I figured the best way to start is, well, let's actually just talk about the experiment first. It's called Xenon 1T. And it's actually one of the more advanced versions of the original Xenon experiment that's essentially trying to discover all of these mysterious particles that are very difficult to detect, such as particles that could be responsible for the mysterious dark matter. The way it works is by using a relatively large tank filled with xenon, specifically large amounts of liquid xenon that usually doesn't interact with anything. And in this case, over the years, the actual tank has been increasing in size to the point where now we have a tank that's able to hold over 3 million tons of xenon on the inside. At the same time, this tank is placed somewhere really deep in the ground where it's protected from all sorts of interference. And it also contains a lot of very sensitive sensors on the top and usually on the bottom as well. And so what this allows the scientists to do is to basically be able to detect really minute interactions. Even like a single particle passing through this tank, in this case right here, would then be producing enough interaction with xenon that it would then be detected by these really sensitive sensors, which would then be able to create a three-dimensional picture of where this particle passed through. And because this detector is so sensitive and because it's able to pretty much detect absolutely everything, it's always very hard to actually protect us from unneeded interference. Like for example, from interaction with particles that we're not really looking for and that we already know a lot about. And so over the years, the scientists have created a kind of a baseline for what they expect to discover in these experiments based on the particles we already know about. So anything over this limit, over the expected values, will obviously create a lot of questions. And in this particular case, the scientists expected, theoretically, to discover about 232 interactions in the xenon detector over the period of its activity. The thing is, when they actually looked at the data and when they started to calculate how many different events were discovered, they realized that there were more, 53 more to be exact. And in this case, what they were actually seeing had the energy equivalent to several different concepts that were previously theoretical, including these so-called solar axions, which have previously been also used as a kind of explanation to the mysterious dark matter. So this is where things kind of get a little bit more complicated, because first of all, what exactly is an axion? So a few decades ago, when studying the concept of symmetry in the universe, or basically that everything for the most part seems to be symmetric everywhere, the particle physicists realized that when it comes to the actual subatomic particles and subatomic forces, the so-called strong force should technically be not symmetric. Now, it's a very difficult concept to explain in a single video, but the idea here is that mathematically and physically, it's more beneficial for different subatomic particles to not really have this symmetry going on. But the thing is, we don't really see it. When it comes to the strongest force, for example, the so-called strong force that holds protons and neutrons together, it really should not be symmetrical at all. And if it's not symmetrical, we should be observing a lot of other effects in the universe that we're not seeing, such as, for example, the neutrons should have magnetic charge, which they don't. But that's a really simple explanation here, and if you want more detail, you can check out the PBS video that should be linked somewhere in the description. The explanation there is a little bit more thorough, but also a little bit more complex. Now, axions, the mysterious particles that we've never been able to detect, would totally explain all of this away. The existence of mysterious axions would explain how subatomic particles and subatomic forces are able to maintain this symmetry, and would actually explain how everything kind of works together. The problem here is that we've never been able to see these axions, we've never been able to detect them. And that's actually by their design. A typical axion would have no electric charge, it would have an extremely small mass, it would barely interact with anything at all, but according to the theories of axions, they would all be produced, for the most part, during the early existence of the universe, during the Big Bang. And there would be so many of them produced that they could easily explain the effects of dark matter we're seeing around the universe. So even though they don't interact with anything, their actual sheer numbers would be more than enough to explain the actual dark matter we're seeing around the universe. While at the same time, they also take care of the so-called CP symmetry, or the symmetry of the strong force, which has not really been explained just yet. So in other words, these axions would take care of two problems, and because of that, back in the days, one of the scientists decided to propose the name axion, which was also a name for a detergent, which basically cleans your clothes. So in that sense, because it clears up so many problems, one of the scientists thought that this is a perfect name for this subatomic particle. But because we've never actually seen them, we've only had a few proposals for different experiments to try to detect these axions. One of the more interesting experiments that tried to discover axions was actually by using their very interesting property where an axion can turn into a photon and then back to axion if a magnetic field is applied to it. The wonderful person by the name of Axel Lindner created this illustration that shows you how this works. Essentially, if you were to shine a light onto a typical wall with electromagnetic force applied right here in front of the light, we expect some of these light particles to turn into axions and to essentially pass through the wall. And then if on the other side you do the same thing and now use the electromagnetic field to try to turn the axions into light, you should technically be able to detect some of the light coming through the wall. In other words, by design, axions should allow light to pass through walls, and we should be able to see things coming through walls all the time. But the thing is, we don't see that, and a lot of these experiments so far have failed. And mostly because we think that it's just very difficult for axions to interact with matter, even when we try to force them to interact with that matter. And so the experiments so far have not really been that successful. but one of the experiments expected to find axions using the xenon detector I previously mentioned. And specifically because we also expect the biggest light producer near us, our Sun, to produce lots and lots of these axions, and a lot of them should be passing through Earth right now as I'm speaking. Essentially, we expect axions that are created inside the Sun because it has a lot of magnetic field and it has a lot of photons to eventually be detected here on Earth if we wait long enough and if we use a sensitive enough detector. And because Xenon 1T detector did have these unusual 52 events that cannot be explained in any other way right now, that's why some scientists claim that maybe this is what we're seeing. Maybe we actually finally found axions coming from the Sun. But right now we do need to have further investigations because there are two more alternative propositions. One of the possible explanations is that there is a slight chance the tank may have been contaminated with an isotope of hydrogen known as tritium. Even a single atom of tritium would actually produce very similar effects that we observed in this particular experiment. The other explanation involves the mysterious neutrinos and the idea that maybe we just don't understand neutrinos very well. Neutrinos can also pass through the xenon detector because they normally don't interact with matter as well as other particles, and so if they actually have slightly different properties from what we initially thought, maybe that's their fault. Maybe they were responsible for these unusual detections. But nevertheless, the best explanation right now, the most likely explanation at least, are the axions. They have the highest chance of being responsible for what the scientists observed in the xenon tank, and the only possible source for these axions would be our Sun. So technically we refer to these as the solar axions. But does this mean that we finally found the mysterious dark matter and we finally know what it is? Well, not just yet. The Xenon experiment still has at least one more upgrade to go through, and this will allow us to kind of really narrow down what we've found here and what's basically causing these unusual observations. Once we can identify exactly what caused these observations, we'll be able to tell for sure if what we just saw was dark matter. But as of right now, as of 2020, this has been the best chance for us to discover the mysterious dark matter, and if axions have indeed been discovered just now, this would clear up a huge amount of problems for the particle physics and would allow us to understand the universe in a lot more detail as well. Right now, we sort of depend on the axion existence for essentially understanding the universe, and without their existence, things get a little bit more complicated. But anyway, whether this was the signs of dark matter or something completely different, there are still going to be more investigations about these particular detections, and they will definitely lead to something exciting in the future. Hello wonderful person, this is Anton, and today we're going to be talking about what seems to be a resolution to one of the mysteries in the universe. The mystery of galaxies that seem to possess almost no dark matter whatsoever. Or at least one of these galaxies we've discovered 2 years ago that was very different from everything we've seen in the universe. The galaxy that possessed very little to possibly no dark matter. The mystery that we discussed about 2 years ago. But now we seem to have a conclusive evidence suggesting we kind of know what exactly happened there and can possibly explain other galaxies as well. So let's talk a little bit more about this in a little bit more detail. Beginning with the first assumption that dark matter is some kind of a particle or some kind of a substance surrounding the galaxies in the way you see in the picture here. It's the stuff in blue. We don't really know what it's made of, we don't really know what exactly or how exactly it behaves compared to the other matter in the universe, but we know it doesn't seem to interact with a lot of things. And it only seems to interact with regular matter through gravity. And all of this mathematically and also physically makes total sense. But because we're having trouble identifying the exact particle, that's why some people stop believing in it. Although this is not really a matter of belief. It's the matter of observation, and observational evidence definitely suggests that dark matter is real. But anyway, there are so many other videos on the channel that talk more about this. Today let's focus on these mysterious galaxies. So only roughly around a year ago, we actually discovered 19 more of these unusual galaxies, which were all surprisingly lacking dark matter. And the reason we knew so is because of various globular clusters we were able to identify and analyze in these galaxies, and then when comparing this to the mass of visible matter, that is stars and gas, we realized that it was just lacking a lot of the mass, and that mass was supposed to be dark matter mass. There was unfortunately no better explanation other than they seem to be lacking dark matter. And the best example is the galaxy you see right here. This is the picture taken by Hubble. This is the galaxy known as NGC 1052 DF4. NGC 1052 is actually the larger galaxy next to it, the galaxy you see on the left. The spiral galaxy on the right is known as NGC 1042. But right between them, somewhere in the darkness of space, there are actually several other dwarf galaxies, and one of them kind of looks like this. And this is essentially one of these galaxies that seems to be lacking dark matter. It also has a neighbor, NGC 1052 DF4, which also was found not so long after and also seemed to be lacking dark matter as well. And several different studies tried to see if they can explain this differently, and so far every study seemed to have confirmed the lack of dark matter in these galaxies. In other words, they seem to possess only visible matter, only stars and gas, and overall their mass is very, very small. So the stuff that usually represents the majority of the mass in a galaxy is totally not there. And also, just for fun, I wanted to show you this picture from a study we recently discussed as well, not so long ago. And this is another dwarf galaxy where the situation is pretty much the opposite. This galaxy has a tremendous amount of dark matter. As a matter of fact, it's almost as massive as the Milky Way galaxy. But notice how they actually kind of look similar. They both contain very, very small amounts of visible matter and stars, but in terms of the total mass, they're completely different. We're talking about like thousands and thousands of times difference. And so that's why trying to analyze and understand how all of this works is something a lot of scientists have been trying to do for the past 2 years. Now, the mystery of this dark matter galaxy, the one that has a lot of dark matter, has recently been solved. You can check out the video about this somewhere over there. But so what's happening with these things? And also, why is it so surprising that the galaxy has no dark matter? And the reason is in our explanations for how the universe formed and in how different galaxies structure themselves and stuff around them. All of the computer simulations we have and pretty much all of the analysis so far requires dark matter to be a kind of a foundation for various gas and for various stars to be formed, thus creating the galaxies. In essence, the fabric of the universe itself, the actual structure of the universe, depends directly on the presence of dark matter. The cosmic web, the galaxies, everything in those galaxies, all of the clusters, they have to have dark matter as a kind of a building block in the beginning for everything else to kind of get stuck to it and then start forming. So no dark matter means no galaxy should exist there. So how did this come to be if it has no dark matter in it? Is this some sort of an anomaly, some sort of a strange creation that defies physics? Or is it something very, very easy to explain? And it turns out it's the latter. Turns out that it's actually pretty easy to explain where dark matter went. All of this thanks to amazing new observations coming out of Hubble telescope that was able to focus on this location for a pretty long time, allowing us to discover more stuff in this region and thus analyze what's really happening here. Although actually another observatory known as Tide Observatory was used for this as well, using the telescope known as IAC-80, which allowed us to take this picture here, with the galaxy in question being right in the middle. Now, first of all, the galaxy known as NGC 1052, in terms of the space distances, in terms of galaxy distances, is actually not that far from us. You could technically see it if you had a telescope, but its tiny neighbor that's about 45 million light years away from Earth is unfortunately very, very difficult to see because there's just not enough stars here. So you really need to have a very powerful telescope, like, I don't know, some kind of a space telescope, for example, to be able to see what's going on here in detail. And well, let's try to answer this mystery once and for all. So what's happening here? Well, according to the scientists in this paper, the culprit and the answer to the mystery is actually right here, another galaxy. The galaxy known as NGC 1035. Apparently, this galaxy right here is breaking apart the nearby dwarf galaxies and is essentially what's known as tidally disrupting them. It's basically doing this. Because of the tidal forces coming from the larger, more massive galaxy, the smaller galaxy is basically being slowly stripped apart. It's also being spaghettified to some extent. But in this particular case, it seems that the tidal disruption started with the dark matter. The dark matter was essentially grabbed and stretched away from the galaxy, leaving behind all of the stars. Which of course kind of makes sense because dark matter is distributed over a much larger volume and is more likely to be sort of sucked out of the galaxy first. Although maybe not everything here is so clear-cut and not everything makes sense just yet. But how did they even discover all of this? Well, what the scientists did is what we usually do. They looked for more globular clusters. They tried to identify as many globular clusters in the vicinity of this galaxy and tried to see what those globular clusters were doing in regards to the galaxy and in regards to the nearby neighborhood. And normally, because globular clusters are so compact and they have so many stars in them, they're relatively easy to discover, and at the same time they normally represent very major times in the galaxy when suddenly a lot of stars were formed. So by studying globular clusters, we can usually see what's happening to the galaxy, and we can also see if there were any major galactic collisions or other galactic events. So for example, that's how we know that the Milky Way galaxy had several collisions in its past. We know there's about 150 of globular clusters, around 150, in the Milky Way, and by studying them we can kind of study the history of Milky Way. So by studying these things in other galaxies, we can generally discover what's happening in them as well. And the current alignment of these clusters suggests that the galaxy is currently being stripped, tidally stripped by something else massive, and kind of pointing toward the nearby NGC 1035. Several so-called tidal tails were also identified, suggesting that this is indeed what's happening to this particular galaxy. It's being shredded or tidally stripped apart by another massive object. And although most of the galaxy is still intact, about 7% of the visible mass has already left the galaxy and is being slowly, well, I guess you can call it spaghettified, but basically it's being scratched apart by the tidal forces from NGC 1035. With the major implication in the study being that the dark matter has already left the galaxy. In other words, it left first, and now all of the mass is following it as well. And we've actually seen these disconnects between visible matter and dark matter in the past as well. The best example is in the bullet cluster, where the visible matter and the dark matter interacted slightly different from one another. And so it shouldn't really come as a surprise that somehow the galaxy was first stripped of dark matter and is now being stripped of stars, with the more compact stars in the middle still sort of sticking together, but eventually they will also be all kind of stripped apart and most likely either become part of the NGC 1035 or become lonely rogue objects moving across the universe. But this only solves the mystery for this particular galaxy. We are not entirely sure if this is what happened to the other 19 galaxies, but chances are that that's maybe what's happening to them as well. It's maybe some sort of a tidal stripping effect from the nearby massive galaxies. And also by solving this one mystery, we can now sort of officially confirm that no physics were broken when we discovered this galaxy, and also nothing unusual that we don't know is happening in any of these galaxies to begin with. They're not lacking dark matter for any other reason other than it was just being stolen from them by something more massive and more influential. Something that we know naturally happens everywhere in the universe. Galactic collisions. And so in that sense, this is actually really good news. We were able to solve a very important mystery without changing any laws of physics or coming up with some other unusual dark blank. Anyway, so that's a pretty cool discovery, definitely something to look forward to, especially as it's confirmed or as new discoveries are made in regards to this galaxy. For now though, check out the paper in the description below, subscribe if you still haven't, share this video with someone who loves learning about space and sciences, and most importantly, come back tomorrow to learn something you may have not known before. Maybe support this channel on Patreon or by buying the Wonderful Person t-shirt, and either way, I'll see you tomorrow, space out, and as always, bye bye.